What if I told you there are places in the universe where a single teaspoon of matter weighs as much as a mountain, where gravity twists space and time into knots so tight, even light can't escape? These aren't science fiction, they're real, lurking in the cosmic shadows, defying everything we think we know about reality. From the crushing depths of neutron stars to the bottomless pits of black holes, the universe is packed with densities so extreme, they stretch the limits of physics itself. And today, we're diving headfirst into 50 of the most mind-bending examples. Picture this, a star so dense, its leftover core smaller than a city contains more mass than our sun. A sugar cube-sized piece of it would weigh 1 billion tons on Earth. That's the insanity of a neutron star, where atoms are squeezed so tightly, they collapse into a sea of pure neutrons. But that's just the start. Black holes take density to another level entirely, warping space into a one-way door where time slows to a crawl. And what about quark stars? These theoretical cosmic oddballs might be even stranger, where matter gets shredded into its most fundamental building blocks. The universe doesn't play by gentle rules. It's a brutal, beautiful arena where matter gets pushed to its absolute breaking point. This is a journey to the edge of what's possible, where the familiar laws of physics start to crumble. We'll explore how these extreme densities shape the cosmos, from rippling gravitational waves to the birth of galaxies. You'll discover why a black hole singularity might not even be a thing in the way we understand it, and how scientists use pulsars, cosmic lighthouses made of spinning neutron stars, to map the universe. So buckle up. By the end of this, your jaw will drop at least 50 times, because out there in the infinite dark, the universe is doing things so wild, they'll make you question everything. Ready? Let's go. The crust of a neutron star is a place where physics takes a vacation from everything we consider normal. Imagine taking a single sugar cube's worth of material from its surface. That tiny fragment would weigh more than Mount Everest. How is that even possible? It all comes down to the brutal force of gravity, so intense that it smashes atoms into oblivion. Under normal conditions, atoms are mostly empty space with electrons whirling around a tiny nucleus. But here, gravity doesn't just press down. It annihilates the gaps, crushing protons and electrons together until they merge into pure neutrons. This is what scientists call degenerate matter, a state so dense that the rules of ordinary chemistry cease to exist. Think of it like taking a sponge and squeezing it with the force of 1,000 hydraulic presses until every pocket of air vanishes. That's essentially what happens inside a neutron star's crust. Atomic structures collapse into a uniform ocean of neutrons, packed shoulder to shoulder with no room left to breathe. The pressure is so extreme that even atomic nuclei, normally sturdy, dissolve into this neutron soup. And this is just the outer layer. Dive deeper, and things get even weirder, with theories suggesting the core might contain exotic particles like hyperons or free-floating quarks, breaking matter down into its most fundamental ingredients. What's truly mind-blowing is that this crush of gravity doesn't just stop at reshaping matter. It bends the very fabric of space-time. The surface of a neutron star is so smooth that if you could shrink one to the size of a marble, its imperfections would be no taller than a single sheet of paper. Yet, despite this smoothness, the gravitational pull is so fierce that light itself struggles to escape, warping into curved paths as it tries to climb away. These stars aren't just cosmic oddities, they're extreme physics labs, giving us glimpses into the universe's most unforgiving environments. And the wildest part, we've only begun to understand them. But if you think neutron stars push matter to its limit, wait until you meet their darker, more destructive cousins, black holes. At the heart of every black hole lies a mystery so profound it stumps even the brightest minds in physics, the singularity. This isn't just an ultra-dense object, it's a point where density becomes infinite, where space and time cease to behave in any recognizable way. Imagine taking all the mass of a star or even an entire galaxy and crushing it down to a speck with zero volume. The equations of general relativity scream in protest at this idea, predicting that gravity there becomes so strong, it warps the fabric of reality itself into an infinitely deep pit. What does that even mean? Picture a stretchy rubber sheet representing space-time. Place a bowling ball on it and it creates a dip. That's how planets and stars curve space. Now imagine that dip turning into a bottomless needle-thin spike, piercing clean through the sheet. That's the singularity, a place where the curvature of space-time becomes infinite, where our understanding of physics hits a wall. Even Einstein's theory of relativity, which handles gravity's extremes beautifully everywhere else, collapses here. It's not just that we don't know what happens inside, it's that the math tells us the concepts of inside and outside might not even apply anymore. And here's where things get even weirder. A black hole singularity isn't some solid, tangible object floating at the center. It's more like a cosmic glitch in the universe's code, a place where matter doesn't just get compressed, but where the very idea of matter might unravel entirely. Some theories suggest the singularity could be a gateway to other universes. Others propose it's a knot of pure energy where quantum mechanics and gravity finally collide. But the truth is, we may never know for sure because anything crossing the event horizon, the point of no return, is lost to us forever. This is why black holes are more than just cosmic vacuum cleaners. They're laboratories for the most extreme physics imaginable, pushing us to rethink everything from the nature of time to the origins of the universe. And while the singularity remains hidden behind the ultimate cosmic curtain, studying its shadow, through phenomena like Hawking radiation or the bizarre firewall paradox, gives us tantalizing hints about what might lurk in those infinite depths. One thing's certain, the universe loves extremes, and nothing's more extreme than a place where the rulebook burns to ash. While black holes and neutron stars represent the universe's most extreme densities, white dwarfs offer a slightly less terrifying, but no less fascinating example of cosmic compression. Imagine taking the entire mass of our Sun and stuffing it into a sphere no bigger than Earth. That's the reality of a white dwarf, the glowing ember left behind when a star like ours exhausts its nuclear fuel. The physics at play here are just as extreme, but instead of neutrons holding everything together, it's a quantum quirk called electron degeneracy pressure that keeps these stellar remnants from collapsing further. Here's how it works. Under normal circumstances, electrons orbiting an atom's nucleus follow strict rules, refusing to occupy the same quantum state. But when a dying star sheds its outer layers, gravity crushes what's left with such force that electrons are squeezed shoulder to shoulder, forming a dense, quantum-resistant sea. Picture a packed subway car where no one can move except in this case. The passengers are electrons, and their refusal to occupy the same space creates an outward pressure so powerful it holds gravity's crushing grip. This bizarre quantum standoff creates a star with a density of about 1 ton per cubic centimeter. A single sugar cube of this material would outweigh a car on Earth. What makes white dwarfs especially intriguing is their fate. Unlike neutron stars or black holes, they don't have an endless reservoir of mass to push them past their limits. But if they siphon enough material from a companion star, electron degeneracy pressure can suddenly fail in a cataclysmic explosion known as a Type 1, a supernova, one of the most energetic events in the universe. Otherwise, they cool cool over trillions of years, fading into cold, dark spheres of crystallized carbon and oxygen. Yet even in their quiet demise, white dwarfs hold cosmic secrets. Their predictable brightness makes them ideal standard candles for measuring galactic distances, while their composition reveals the chemical history of the universe. They're proof that even in death, stars continue to shape the cosmos, not through sheer destructive force, but through the subtle, relentless laws of quantum mechanics. And that's a density story with a surprisingly elegant twist. But what if neutron stars aren't the end game when it comes to cosmic density? Enter the quark star, a hypothetical monster that takes crushing matter to an even more extreme level. Imagine a neutron star's core, where gravity's grip is already so strong it turns atoms into a sea of neutrons. Now crank that pressure up another notch until even those neutrons shatter like glass under a hammer. What's left? A swirling soup of quarks, the fundamental particles that normally live locked inside protons and neutrons floating freely in a state known as quark-gluon plasma. This is matter stripped down to its barest ingredients, a cosmic broth denser than anything we've ever observed. Quark stars could form when neutron stars absorb extra mass, maybe from a companion star or a catastrophic collision pushing their cores past the breaking point. The transition wouldn't be gentle. It's like stacking weights on a diving board until it snaps. Suddenly, neutrons disintegrate, releasing their quarks from confinement. The result, a star even smaller and denser than a neutron star, where a single teaspoon of material could outweigh an entire skyscraper. Theoretical models suggest quark stars might have a surface harder than diamond, forged under pressures so intense they mimic the conditions of the universe's first microseconds after the Big Bang. Scientists hunt for these elusive objects by studying strange cosmic signatures. Some neutron stars emit pulses of energy that don't quite fit the usual models. Could those anomalies be quark stars in disguise? Others look for fleeting bursts of neutrinos, ghostly particles that might stream out during the instant a neutron star cracks open into quark matter. And then there's the gravitational wave angle. If two quark stars merged, the ripples in space-time they'd create would carry a unique fingerprint, unlike anything produced by neutron stars or black holes. But here's the twist: quark stars might not stay quark stars forever. Under certain conditions, their cores could collapse even further, forming a black hole in a cosmic domino effect. Or more bizarrely, they might stabilize into strange stars, hypothetical objects where quarks transform into an exotic, strange quark variant, creating matter so stable it could outlast the universe itself. The wildest part, if strange stars exist, they might be infectious. A single collision could convert normal matter into strange matter, triggering a chain reaction that reshapes entire galaxies. For now, quark stars remain just beyond the edge of our telescopes, a tantalizing what if at the frontier of astrophysics, but their potential existence forces us to rethink how matter behaves under extremes. After all, if crushing a star into neutrons isn't the universe's final trick, what else is hiding in the cosmic shadows? One thing's certain: the deeper we dig, the stranger the answers get. Deep beneath Jupiter's swirling bands of gas lies a mystery that defies our planet-bound instincts. A core so dense and strange, it reshapes everything we know about giant planets. While Jupiter appears as a vast ball of hydrogen and helium, its heart hides a secret: layers of metallic hydrogen, crushed under pressures so immense that this normally lightweight gas transforms into something resembling liquid metal. At these depths, hydrogen atoms shed their electrons, creating a thick, conductive soup that flows like mercury, but with densities up to 10 times greater than solid lead. This isn't just a curiosity, it's the engine behind Jupiter's jaw-dropping magnetic field, 20,000 times stronger than Earth's. Picture the metallic hydrogen layer as a colossal dynamo, spinning with the planet's rapid rotation. As this electrically charged fluid churns, it generates currents that wrap Jupiter in a magnetic shield so powerful, it deflects solar winds and traps radiation with enough intensity to fry spacecraft electronics. The Juno mission's data revealed just how chaotic this magnetic field is, with irregularities suggesting the metallic hydrogen layer isn't uniform but lumpy, like a pot of boiling metal stirred by invisible forces. What's truly staggering is the pressure needed to create this state. At Jupiter's core, the weight of thousands of miles of atmosphere presses down with the force of millions of Earth's surface pressures. Under these conditions, even hydrogen, the lightest element, gets squeezed so tightly that its electrons break free, turning it into a superconductor. Some theories suggest the innermost core might harbor heavier elements like rock and metal, compressed into exotic states we've never seen. Imagine diamonds dissolving into a sea of ionized carbon or silicate minerals behaving like molten glass under these extremes. Yet Jupiter's core isn't just a static lump. It's a dynamic, heat-radiating beast, possibly still holding onto warmth from the planet's formation over 4.5 billion years ago. This internal furnace drives storms the size of continents and sustains jet streams that rip through the atmosphere at speeds topping 400 miles per hour. The Great Red Spot, it might owe its centuries-long lifespan to energy rising from this hidden realm like steam fueling a hurricane. Here's the kicker: we've never directly observed metallic hydrogen on Earth. Lab experiments have come close, using diamond anvils to crush tiny samples, but Jupiter's scale is unimaginable. A planetary pressure cooker where this exotic matter exists in oceans, not pinpricks. Studying it isn't just about understanding one planet, it's a window into the birth of solar systems. Gas giants like Jupiter likely formed first, their cores acting as seeds that gathered the gas and dust to build our cosmic neighborhood. So while Jupiter's storms steal the spotlight, its hidden heart is the real marvel, a place where matter twists into forms that blur the line between gas and metal, where the universe bends the rules just to see what happens. And if that's what lurks inside our solar system's king of planets, imagine what secrets lie within the gas giants orbiting distant stars. At the heart of almost every large galaxy, a monster lies in wait, a supermassive black hole so vast it defies comprehension. Take Ton 618, one of the most massive black holes ever discovered. This cosmic titan weighs in at a staggering 66 billion times the mass of our Sun, crammed into a space no larger than our solar system. Wrap your mind around that for a second: billions of stars worth of matter, crushed into a volume where the very concept of space might no longer apply. These behemoths don't just sit quietly, they feast. When a star drifts too close, tidal forces stretch it like taffy in a process called spaghettification. The star's outer layers get shredded into glowing ribbons of plasma, swirling into the black hole's accretion disk at near light speeds. Friction within this disk heats the material to millions of degrees, creating some of the brightest flares in the universe, quasars that outshine entire galaxies. Ton 618's quasar burns with the luminosity of 100 trillion suns, a beacon visible across 13 billion light-years of space. But here's the twist: black holes like this aren't just cosmic vacuum cleaners. They're messy eaters. As matter spirals inward, magnetic fields twist it into jets that blast outward at relativistic speeds, carving bubbles in intergalactic gas that span millions of light-years. These jets are so powerful they can shut down star formation across entire galaxies, proving that supermassive black holes don't just consume, they reshape their cosmic neighborhoods. What's truly chilling is how these giants grow. Mergers with other black holes play a part, but their primary diet might be cold gas clouds funneled inward by galactic collisions. Some theories suggest they could also feed on dark matter, a shadowy buffet we've yet to fully understand. And despite their appetites, supermassive black holes obey a strange cosmic speed limit, the Eddington rate, where radiation from their meals pushes back against incoming matter like a stellar-scale hovercraft. Exceed this limit, and they literally blow their own dinner away. Yet somehow, Ton 618 and its kin reached sizes that challenge physics itself. Their existence hints at feeding frenzies in the early universe, where conditions allowed black holes to balloon faster than we thought possible. Some might have formed from direct collapse, seed, black holes, primordial giants born when entire clouds of gas collapsed without ever forming stars. Others could be evidence of exotic physics, like black holes consuming not just matter, but the fabric of space-time itself. One thing's certain, these gravitational overlords hold galaxies hostage. Their gravity dictates the motion of stars thousands of light years away, and their outbursts can sterilize whole swaths of space. Yet without them, galaxies like our Milky Way might never have formed. They're destroyers and architects, both prison and scaffold for the universe's grand design, proof that density, taken to extremes, doesn't just bend the rules. It rewrites them. Some neutron stars spin so fast they defy the very laws that govern ordinary matter. Imagine a stellar corpse the size of Manhattan whirling 700 times every second its equator, racing at nearly a quarter the speed of light. This isn't science fiction, it's the reality of millisecond pulsars, cosmic dynamos where extreme density meets mind-bending rotation. How does something so massive spin without tearing itself to shreds? The answer lies in the very thing that makes neutron stars so bizarre, their incomprehensible density. When a massive star collapses into a neutron star, it carries with it the original star's angular momentum, the same way a figure skater spins faster by pulling their arms in. But here, the compression is so extreme that a star once millions of kilometers wide shrinks down to about 20 kilometers across. That's like taking Earth's entire rotation and cramming it into a spinning coffee mug. The result, a celestial gyroscope locked in a hyper-fast pirouette, where a single misstep in physics would mean instant disintegration. What keeps these stars intact is the sheer gravitational grip of their own density. At their cores, matter is packed so tightly that gravity overpowers even the centrifugal forces trying to fling them apart. Picture trying to spin a water balloon until it bursts. Now replace the water with concrete, then with neutron star material 100 trillion times denser. That's the difference between ordinary objects and these cosmic speed demons. Their gravity is so strong, even light struggles to escape, let alone chunks of the star's surface. But the real magic happens when these spinning neutron stars become pulsars. As they rotate, their powerful magnetic fields funnel radiation into narrow beams, sweeping across space like lighthouse beams. From Earth, we detect these as precise pulses of radio waves, blips so regular they rival atomic clocks. Some millisecond pulsars, spun up even faster by siphoning gas from companion stars, achieve timing so precise that scientists use them to test Einstein's theory of relativity. A single pulsar's rhythm, monitored over years, can reveal the subtle stretching of space-time caused by passing gravitational waves, yet even these speeds have limits. Push a neutron star toward 1,000 rotations per second, and the outward force of spin begins to challenge gravity's hold. Some theories suggest there might be an upper boundary, a point where the star's crust cracks under the strain, releasing catastrophic starquakes or even triggering a collapse into a black hole. Others speculate that the fastest pulsars could be wrapped in mountains of solid neutron matter, mere millimeters tall but weighing more than Mount Everest, their peaks trembling under the star's insane rotation. This is the universe showing off, taking the familiar concept of spin and dialing it up to extremes only possible where matter exists on the knife's edge of oblivion. These pulsars aren't just cosmic curiosities, they're natural laboratories pushing the boundaries of how we understand physics under conditions no lab on Earth could ever replicate. And every time one of their rhythmic pulses reaches us, it carries with it a message from one of the most unforgiving places in existence. Dark matter doesn't just drift through space like a ghostly fog. It might gather in dense, invisible knots so massive they warp the cosmos from the shadows. Picture an entire mountain range made of something you can't see, touch, or even detect directly. Yet its gravity tugs at stars and bends light like a cosmic puppeteer. These hypothetical dark matter clumps, sometimes called dark matter halos, could be the universe's best-kept secret, shaping galaxies in ways we're only beginning to unravel. How does something so elusive clump together? Think of it like this: ordinary matter, the stuff of planets and stars, collides, sticks, and eventually collapses under gravity. But dark matter doesn't play by those rules. It's thought to be cold, meaning its particles move sluggishly, allowing gravity to herd them into dense pockets over billions of years. Without the friction or pressure that slows regular matter, these clumps could condense into structures far denser than anything made of atoms. Some theories suggest they might even collapse into dark stars, hypothetical objects powered not by nuclear fusion but by the annihilation of dark matter particles themselves. The evidence for these clumps is written in the motions of galaxies. Stars on the outskirts of spiral galaxies orbit too fast for the visible matter to explain, as if something unseen is anchoring them with extra gravity. Even weirder, when light from distant galaxies passes near these invisible halos, it bends in a phenomenon called gravitational lensing, revealing the presence of mass we can't see. The most dramatic examples are dark galaxies, entire systems where dark matter outweighs normal matter by hundreds to one, leaving behind only faint whispers of stars. But here's where it gets wild. If dark matter clumps are as dense as some models predict, they could harbor dark matter black holes, primordial monsters born in the early universe, lurking undetected. Others speculate that dark matter might form exotic states under extreme pressure, like a superfluid or a crystalline lattice, defying every analogy we have for matter. And then there's the eerie possibility that these clumps occasionally brush past ordinary matter, leaving behind unexplained bursts of energy or even triggering star formation in their wake. The hunt for dark matter clumps is like trying to map a city using only the echoes of footsteps. Scientists scour gravitational lensing patterns, simulate cosmic evolution on supercomputers, and even listen for the faint ping of dark matter particles colliding in underground detectors. Every unexplained wobble in a star's path, every distortion in a galaxy's shape could be a clue. One thing's certain: if these invisible titans exist, they're rewriting the rules of the cosmos from behind the scenes, proof that density isn't just about what we can see, but what we can't. Before galaxies, stars, or even atoms existed, the entire universe was crammed into a space smaller than an atom, a single point of infinite density called the Big Bang singularity. This wasn't just a tight squeeze, it was a state so extreme that time, space, and the laws of physics as we know them didn't yet apply. Picture every star, every planet, every speck of dust in today's cosmos, over 2 trillion galaxies worth of material compressed into a volume with 0 dimensions. The temperature, a number so large it's meaningless, hot enough to fuse every fundamental force into one indistinguishable superforce. The singularity isn't just a dense object in the way we think of neutron stars or black holes. Those have measurable, if absurd, densities, say 1 billion tons per teaspoon. The Big Bang singularity, its density was literally infinite, a mathematical concept that makes even physicists pause. How does something with no volume contain all the energy that would eventually become the observable universe? The answer lies in the explosive expansion of space itself. In the first fractions of a second, space inflated faster than light, stretching that primordial infinity into something finite and measurable, like blowing up a balloon with the entire universe painted on its surface. What's wild is that the singularity isn't just a one-time event. Every black hole harbors its own version, a point where matter crunches back into infinite density. Some theories suggest the Big Bang might have been the other side of a black hole's collapse in another universe, a cosmic recycling of singularities. Others propose that the singularity wasn't a point at all, but a ripple in a higher dimensional brain that ignited our universe like a match striking a cosmic tinderbox. Yet the most baffling part isn't the singularity itself, it's what came immediately after, within the first trillionth of a second. the universe underwent a phase called inflation, where space expanded exponentially, smoothing out wrinkles that would later become galaxies. Quantum fluctuations in that microscopic fireball became the seeds for everything we see today. Your body, your phone, the farthest quasar, all trace back to microscopic ripples in that infinite density. The singularity is the ultimate reset button for physics. No equations can describe it, no analogies can capture it. It's the one moment where the universe reminds us, for all our knowledge, some things remain beyond the edge of understanding. And that's the paradox. The densest thing imaginable gave rise to the vast, sparse cosmos we call home. Take a neutron star's crushing density, then amplify its magnetic field to levels that seem ripped from science fiction. That's a magnetar. These cosmic powerhouses boast magnetic fields 1,000 trillion times stronger than Earth's, so intense they don't just bend metal, they twist the very fabric of reality. At close range, their magnetic pull is so ferocious, it would strip electrons from atoms, reshaping matter into elongated, needle-like chains. If a magnetar hovered halfway between Earth and the Moon, its field would liquefy your credit card's magnetic strip from 100,000 miles away and scramble every hard drive on the planet. What creates such monstrous magnetism? When a massive star collapses into a neutron star, its original magnetic field gets concentrated into a volume millions of times smaller. Picture a giant balloon covered in compass needles. Now crush it to the size of a marble and watch those magnetic lines compress into a chaotic frenzy. But magnetars take it further. Their interiors might host a quantum phenomenon called flux tubes, where magnetic fields become so dense they knot themselves into ropes of pure energy. These tubes could snap like overstretched rubber bands, releasing violent starquakes that crack the magnetar's crust and unleash gamma-ray flares brighter than 100,000 suns. One such flare from magnetar SGR 180620 in 2004 actually ionized Earth's upper atmosphere from 50,000 light-years away, equivalent to a cosmic impi. But the real terror lies in their anti-glow. Unlike pulsars, which emit steady beams, magnetars often produce soft gamma repeaters, random, unpredictable bursts that light up space like a strobe. Some theorists suggest these bursts might originate from magnetic reconnection events, where field lines explosively rearrange, unleashing enough energy to vaporize a planet. Yet magnetars don't just destroy, they also illuminate. Their twisted magnetic fields act as cosmic laboratories, revealing how matter behaves under conditions impossible to replicate on Earth. Atoms in their vicinity stretch into pencil-thin rods, and photons, particles of light, split into two under the field's influence, a phenomenon called vacuum birefringence. Even space-time itself warps around them, creating lensing effects that could, in theory, let us peer around their edges like cosmic funhouse mirrors. The strangest part, magnetars might be fleeting. Their apocalyptic magnetic fields decay over millennia, bleeding energy until they fade into ordinary neutron stars or collapse into something even darker. For now, they stand as the universe's ultimate electromagnets, proving that when it comes to cosmic extremes, density isn't just about gravity. Sometimes it's about the invisible forces that twist the rules until they snap. Beneath the orderly fabric of spacetime we experience lies a hidden maelstrom, a frothing, seething chaos called quantum foam. At scales 1 billion trillion times smaller than an atom, the smooth geometry of the universe dissolves into a turbulent storm where space and time lose all meaning. Here, in the realm of the Planck length, spacetime isn't flat or continuous, it's a bubbling ocean of fleeting wormholes, miniature black holes, and virtual particles that blink into existence only to vanish moments later. This isn't just tiny physics, it's reality itself pixelating under the extreme pressures of quantum gravity. Picture the universe's fabric as the surface of a pond. From a distance, it appears glassy and still, but zoom in close enough and you'll see turbulent water molecules jostling violently, bubbles forming and popping in an instant. Quantum foam is like that, except the bubbles are space-time fluctuations so intense they bend the rules of cause and effect. Within these vanishingly small pockets, energy fluctuations can briefly conjure particle-antiparticle pairs from nothingness, thanks to Heisenberg's uncertainty principle. These virtual particles aren't just theoretical, their transient existence leaves fingerprints, like the faint glow they produce near black holes, known as Hawking radiation. But quantum foam gets stranger. Some theories suggest these space-time bubbles might host microscopic tunnels, Einstein-Rosen bridges, or wormholes connecting distant regions of the universe. These wouldn't be the traversable wormholes of sci-fi. They'd snap shut in fractions of a Planck second, crushed by the same violent fluctuations that birthed them. Others propose that at this scale, space-time might resemble a fractal, endlessly detailed no matter how deep you zoom, like a cosmic version of those infinitely recursive mirror images. The real challenge will likely never observe quantum foam directly. The energy required to probe these scales is a quadrillion times beyond what our most powerful particle colliders can muster. Yet its effects might still be detectable. Gravitational wave observatories, sensitive enough to measure space-time ripples from colliding black holes, could one day catch echoes of this primordial chaos. Some models even suggest that if space-time is foamy, high-energy photons from distant gamma-ray bursts should arrive at Earth slightly out of sync, a delay that could reveal the universe's grainy underpinnings. This frenzy at the bottom of reality isn't just academic. It's where Einstein's relativity, with its smooth, deterministic spacetime, collides head-on with quantum mechanics' probabilistic madness. Unifying these two frameworks means deciphering quantum foam's language, a task that could rewrite our understanding of existence. After all, if spacetime itself is unstable at the tiniest scales, what does that say about the solid universe we think we inhabit? The answer might be as unsettling as the foam itself, that beneath it all, reality is less a stage and more a storm. At the heart of every red giant, a silent time bomb ticks, a core of iron growing heavier by the second. This isn't just another layer of stellar material. It's the ashes of nuclear fusion, the point where a star's energy production hits a dead end. For millions of years, these aging stars burned through lighter elements like hydrogen and helium, fusing them into heavier ones and releasing the energy that makes them shine. But when the core fills with iron, everything changes. Unlike lighter elements, iron absorbs energy when fused. It doesn't release it. So as the core swells with this cosmic deadweight, the star's fiery engine sputters to a halt. The collapse begins subtly, without the outward pressure of fusion to counteract gravity's relentless pull. The core contracts, squeezing iron nuclei so tightly they start behaving in ways that defy ordinary physics. At densities surpassing 50,000 tons per cubic centimeter, electrons normally content to orbit nuclei get crushed into protons, transforming them into neutrons and releasing a flood of ghostly neutrinos. This neutron-rich slurry resists collapse briefly, creating an ultra-dense neutron star in the making. But in stars massive enough, even this neutron pressure isn't enough. The core overshoots equilibrium, collapsing further until it reaches a critical threshold, and then rebounds in a cataclysmic shockwave. That rebound is the first note in a stellar death knell. Racing outward at a quarter the speed of light, the shockwave slams into the star's outer layers, heating them to billions of degrees and blasting them into space in one of the universe's most violent spectacles, a type Roman II supernova. For weeks, the dying star outshines entire galaxies, and in that blinding flash, something miraculous happens. The intense heat and pressure forge elements heavier than iron, gold, platinum, uranium, that normal fusion could never create. These atoms get flung into the cosmos, eventually seeding nebulae where new stars and planets form. Here's the twist: the core's fate depends on a razor's edge. If the original star was between 8 and 20 solar masses, the collapse halts at neutron star density, leaving behind a spinning stellar corpse. But if the star was heavier, the core's gravity overpowers even neutron pressure, crumpling into a black hole so voracious, it sometimes swallows part of the outgoing supernova shock before it can escape. What makes this process so astonishing isn't just the destruction, it's the creation. Nearly every atom in your body heavier than iron, the calcium in your bones, the zinc in your enzymes, was forged in these apocalyptic explosions. The gold in your jewelry, likely born in the last frantic seconds of a red giant's core collapse. These dying stars aren't just in points, they're cosmic alchemists, transforming simple elements into the building blocks of planets' life, and even the device you're using right now to watch this video. So the next time you look up at the night sky, remember, the stars you see aren't just lights, they're future supernova, waiting to explode, die, and gift their heavy elements to the universe. Primordial black holes sound like relics from a cosmic horror story, tiny, ancient monsters born in the chaos of the early universe, packing the mass of a mountain into a space smaller than an atom. Unlike the black holes we know today, forged in the collapse of massive stars, these could have sprung into existence in the first frenzied seconds after the Big Bang, when the universe was a seething ocean of unimaginable density and pressure. Picture space itself shuddering under such extremes that random fluctuations, tiny wrinkles in the fabric of reality, collapsed inward, forming microscopic pits of infinite gravity. These wouldn't be the gaping voids we imagine today, but pinpricks of destruction, some as light as a paperclip, yet dense enough to bore through planets like a bullet through smoke. What makes primordial black holes so eerie is their potential invisibility. A black hole with the mass of an asteroid would emit Hawking radiation so faint, it'd take longer than the current age of the universe to evaporate, meaning these things could still be out there, drifting unseen through galaxies. Some might lurk in our own solar system, their gravity subtly tugging at comets or warping the paths of distant probes. Others could be hiding in plain sight, masquerading as dark matter, those elusive clumps of mass that bind galaxies together but refuse to emit light. After all, if the universe is riddled with trillions of these primordial relics, their collective gravity could explain the missing mass scientists have been chasing for decades. But here's where it gets wild. If these tiny black holes exist, they might not always stay tiny. Feed one enough gas, dust, or even stray planets, and it could grow, slowly at first, then voraciously, until it blossoms into a supermassive black hole, the kind we now see anchoring galaxies. That means the darkest giants in the cosmos might have started as quantum-scale specks, swallowing their way up the cosmic food chain over billions of years. Others could be ticking time bombs. A primordial black hole passing through Earth wouldn't just punch a clean hole. It'd send seismic shockwaves through the planet as its gravity rips atoms apart, creating a trail of superheated plasma in its wake. Yet for all their terrifying potential, primordial black holes could also be cosmic keys. Detecting one, perhaps by the flash of radiation as it evaporates or the lensing effect of its gravity on distant starlight, would give us a window into the universe's first moments. Their very existence would force us to rethink inflation, dark matter, even the nature of gravity itself. They're ghosts from a time when the laws of physics were being written, and if we ever catch one, it might whisper secrets about how everything began. Until then, they remain one of the universe's most tantalizing what-ifs, a proof that sometimes the smallest things hide the biggest mysteries. Imagine a city crammed with every building, park, and street from an entire country, somehow condensed into a space no larger than a neighborhood. That's the cosmic absurdity of ultra-compact dwarf galaxies, or UCT. These enigmatic objects blur the line between star cluster and galaxy, packing hundreds of millions of stars into a region just 200 light-years across. To put that in perspective, if our Milky Way were scaled down to match a UCD's density, it would fit inside the orbit of Mercury with room to spare, What makes UCDs truly bizarre isn't just their tight packing, it's what lurks at their cores. While globular clusters, their closest cousins, are held together by the collective gravity of their stars, ultra-compact dwarfs seem to harbor supermassive black holes or bizarre dark matter halos far heavier than expected. Take M60 UCD1, a UCD near the Virgo cluster. Despite being only 300 light-years wide, it contains a black hole weighing 21 million suns, nearly 5 times heftier than the one anchoring our galaxy. That's like finding an aircraft carrier docked in a suburban swimming pool. Their origins are even stranger. Some might be the stripped-down carcasses of normal galaxies, their outer stars torn away during violent collisions with larger neighbors. Others could be failed galaxies, objects that formed with too little gas to grow beyond their compact infancy. Then there's the nuclear theory, that UCDs are the plundered cores of once mighty galaxies, their outer layers sheared off by tidal forces, leaving behind only their densest, most central regions. The leftover debris, a super-dense nugget of stars orbiting like cosmic driftwood. Their discovery rewrote the rules of galactic formation. Before UCDs, astronomers assumed galaxies and star clusters occupied distinct categories, like comparing a sprawling metropolis to a tiny village. But these objects straddle both worlds, proving the universe enjoys bending its own rules. Their very existence hints at unseen processes in galaxy evolution, where mergers, collisions, and gravitational theft sculpt objects we're only beginning to comprehend. Yet the real mystery isn't how they formed, it's how they survive. At such extreme densities, stars should collide frequently, triggering supernova or merging into bizarre superstars. Some UCDs glow with unexpected X-rays, suggesting they're riddled with neutron stars or black holes feasting on wayward stellar material. Others emit far more infrared light than their visible stars can explain, as if cloaked in veils of dust from ancient cataclysms. These galactic overachievers are more than cosmic oddities, they're stress tests for our understanding of structure in the universe. By studying them, we glimpse how gravity behaves when pushed to extremes, how black holes shape their surroundings, and how galaxies can evolve down paths we never imagined. They're proof that sometimes the universe's most fascinating stories come in the smallest packages. When two neutron stars spiral toward each other in a deadly cosmic dance, they don't just collide, they rewrite the periodic table in a blaze of radioactive fury. These ultra-rare events, called kilonovae, are the universe's most extravagant alchemy labs, forging gold, platinum, and other heavy elements in quantities that dwarf a star's lifetime of nuclear fusion. Picture this: two city-sized remnants of dead stars, each so dense that a teaspoon weighs 1 billion tons, whipping around each other hundreds of times per second before finally smashing together. The collision unleashes energy equivalent to a supernova, but with a twist. Instead of just exploding outward, the merging stars fling shredded neutron material into space at nearly light speed, creating swirling, ultra-hot debris clouds where atomic nuclei rebuild themselves into heavier forms. The physics behind this is staggering. As the neutron stars merge, their crushing gravity briefly forms a hypermassive neutron star, a single, unstable object with even more extreme density. But this monster can't last. Within milliseconds, it either collapses into a black hole or explodes, ejecting neutron-rich material in expanding jets. The free neutrons, no longer confined inside atomic nuclei, bombard surrounding atoms in a process called rapid neutron capture, or the R process. This is how cosmic gold gets made. Normal atomic nuclei gobble up dozens of neutrons in nanoseconds, then decay into stable heavy elements. A single kilonova can produce hundreds of Earth masses worth of gold and platinum in minutes, enough to coat every planet in a galaxy with a glittering layer of precious metals. We know this isn't theoretical because we've seen it happen. In 2017, gravitational wave detectors caught the ripples from neutron star merger GW170817, while telescopes witnessed the afterglow, a peculiar violet light that faded to red over days, the signature of radioactive heavy elements decaying. The event ejected material worth maybe $10,000 octillion in gold alone, proving kilonovae are the ultimate cosmic jewelry stores. But kilonovae don't just make bling, they're crucibles for the universe's rarest elements. Tellurium, iodine, even uranium might form in these explosions, elements so heavy they can only be born under the most violent conditions. The ejected material doesn't just float aimlessly. It seeds future generations of stars and planets, meaning the gold in your wedding ring might have been forged in a neutron star collision billions of years before our solar system existed. The aftermath is just as wild. Some mergers leave behind a magnetar, a neutron star with a magnetic field strong enough to erase credit cards from light years away. Others birth black holes that gobble up remaining debris, creating swirling accretion disks hotter than the sun's core. And because neutron star collisions also emit gravitational waves and gamma-ray bursts, they serve as cosmic lighthouses, helping astronomers measure the universe's expansion rate with unprecedented precision. Kilonovae are more than just dazzling light shows. They're proof that the universe's most valuable elements aren't forged in stellar furnaces, but in the wreckage of catastrophic collisions, reminding us that sometimes creation requires destruction on an unimaginable scale. Neutron stars might be the densest objects we can observe, but some theories suggest they're just the tip of the cosmic iceberg. Dive deeper, and you'll find a wild possibility that under unimaginable pressure, even neutrons can't hold their shape. They shatter, releasing their tiniest building blocks, quarks. This isn't just a minor tweak to the rules, it's a fundamental rewrite of how matter behaves at the extremes. Welcome to the hypothetical realm of strange matter, where the very fabric of neutron stars could transform into something even more bizarre: strange stars. Quarks normally never roam free. They're forever locked inside protons and neutrons, bound by the strong nuclear force. But in a neutron star's core, gravity's grip might be strong enough to break those bonds, creating a soup of unattached quarks. Not just any quarks, strange quarks, an exotic variety that's heavier and more unstable than the ones making up everyday matter. If enough of these strange quarks appear, they could trigger a chain reaction, converting the entire neutron star into a strange star, a city-sized orb of pure quark matter, denser than anything we've ever seen. Here's the twist: strange matter might be the ultimate cosmic domino effect. Unlike normal matter, which stabilizes into atoms, strange matter could be more stable in its free quark form. If that's true, any chunk of it touching regular matter might infect it, converting atoms into strange matter on contact. Picture a single grain of this stuff landing on Earth. Theoretically, it could start a runaway reaction, transforming our entire planet into a lump of quark goo. Before you panic, know this: we've found zero evidence of this actually happening, but the fact that it's even possible under the laws of physics is mind-blowing. How would a strange star differ from a neutron star? For one, it'd be even smoother. The surface of a neutron star already has microscopic imperfections, but a strange star's quark surface could be flawless, shaped by forces we've never directly observed. Its gravity would bend light into perfect rings, and its internal structure might vibrate in ways that send bizarre ripples through space-time. Some models suggest strange stars could pulse with quark novas, explosions that outshine supernova when chunks of their surface collapse inward. The hunt for these theoretical objects is already underway. Astronomers scrutinize oddly quiet neutron stars, those lacking the magnetic fields or pulsar activity we'd expect, as potential strange stars in disguise. Others look for bursts of particles that could only come from quark matter annihilation. And deep underground, particle colliders smash nuclei together at near-light speeds, trying to recreate quark-gluon plasma for fractions of a second. If strange stars exist, they're hiding in plain sight, masquerading as ordinary neutron stars while rewriting the rules of reality at their cores. This isn't just about adding another entry to the cosmic bestiary. Strange matter challenges our understanding of stability itself. If quark matter really is the universe's preferred state under extreme pressure, it means everything we see, planets, stars, even our own bodies, are just temporary structures, flimsy by comparison. The neutron stars we marvel at today might be halfway houses on matter's journey to its ultimate form. And that raises a haunting question. In a universe that loves efficiency, why haven't we all turned strange already? The answer might lie in the fragile balance of forces that keeps our familiar world intact for now. The universe's densest objects might not be stars or black holes at all. They could be cosmic cracks in reality itself, thinner than an atom but heavier than entire galaxies. These hypothetical fractures, known as cosmic strings, are thought to be relics from the Big Bang, when the newborn universe underwent violent phase transitions that left one-dimensional scars in space-time. Picture the cracks that form in ice as it freezes, but scaled up to cosmic proportions, except these cracks would carry unimaginable density, packing more mass per inch than a neutron star's core. Unlike black holes, which warp space into three-dimensional pits, cosmic strings would bend the universe in bizarre, two-dimensional ways. Their gravitational pull wouldn't radiate outward in all directions like a planet or star. Instead, it'd be concentrated along their length, creating knife-edge distortions in spacetime. Pass near one, and you wouldn't just feel a tug, you'd experience time itself stuttering, split into parallel streams by the string's gravitational lensing effect. A spaceship crossing a cosmic string's path might emerge with its front half older than its rear, thanks to time dilation so extreme, it'd make a black hole's influence look tame. What gives these filaments such insane density? The leading theory suggests they're frozen energy remnants from when the fundamental forces of nature first split apart during the universe's infancy. As the cosmos expanded and cooled, asymmetries in this energy field could have tangled into ultra-dense threads, each stretching across millions of light years. Some models propose they might even form loops, vibrating like guitar strings and emitting gravity waves detectable across the cosmos, the wildest part. Cosmic strings might not just be theoretical. Some astronomers speculate that odd patterns in the cosmic microwave background, the afterglow of the Big Bang, could be the fingerprints of strings brushing against the early universe. Others hunt for double images of distant galaxies, a telltale sign of a string's light-bending grip. And if two strings crossed or snapped, they'd unleash bursts of energy so powerful they could momentarily outshine entire superclusters. Yet for all their potential ferocity, cosmic strings would be eerily elusive. With widths smaller than a proton, they'd slice through planets and stars like ghostly razor blades, leaving only subtle gravitational ripples in their wake. That's the paradox of these cosmic defects. They could be everywhere, weaving through the universe like invisible spider silk, and we'd never know unless we stumbled right into their gravitational web. Whether they exist or not, their possibility reminds us that the universe's densest corners might not be objects at all, but flaws in the very fabric of existence. Some stars don't just drift through galaxies, they get flung out like cosmic slingshots, racing through the void at speeds that defy imagination. These hypervelocity stars are the universe's runaway projectiles, ejected from the hearts of galaxies with such force that they're flung into intergalactic space at millions of miles per hour. The engine behind this stellar catapult, the supermassive black holes lurking at galactic centers, where gravitational chaos can turn an ordinary star into a speeding bullet. Picture a binary star system, two stars orbiting each other, venturing too close to a black hole's lethal grip. As the black hole's gravity tears the pair apart, one star gets captured, swirling into an inescapable orbit, while its companion is hurled outward at unimaginable speeds. This gravitational slingshot, known as the Hill's mechanism, can accelerate stars up to a staggering fraction of the speed of light. The fastest hypervelocity star ever discovered, S5 HVS1, is rocketing through space at over 4 million miles per hour, fast enough to cross the distance from Earth to the Moon in just 6 minutes. What's astonishing isn't just their speed, but what they survive. These stars endure gravitational forces that should rip them apart, yet their dense cores often come packed, hot, and massive hold firm. Many hypervelocity stars are blue stragglers, stellar oddballs that burn hotter and brighter than expected, possibly forged in the violent mergers of their original binary partners. Others are tough white dwarfs or neutron stars, their extreme density acting like cosmic armor against the black hole's wrath. But their journey doesn't end with ejection. These stars become galactic nomads, streaking through the emptiness between galaxies where few stars dare to wander. Some might even escape their home galaxy entirely, destined to drift alone through the cold abyss of intergalactic space for eternity. Others could someday collide with distant galaxies, their high-speed impacts triggering exotic phenomena like X-ray flares or even new star formation. The real puzzle is how they retain their integrity. The same forces that fling them outward should, in theory, stretch and warp them beyond recognition. Yet hypervelocity stars arrive in one piece, a testament to the resilience of matter under extreme conditions. Studying them gives astronomers a unique window into the dynamics of galactic centers, the limits of stellar structure, and the invisible gravitational tides that shape the cosmos. These runaway stars aren't just cosmic accidents, they're messengers from the most chaotic neighborhoods in the universe, carrying secrets about the forces that launch them into the void. Deep inside a blue supergiant, one of the universe's most luminous and short-lived stars, the core is a pressure cooker where matter gets pushed to its absolute limits. These stellar behemoths, burning dozens of times more massive than our Sun, don't just fuse hydrogen into helium like ordinary stars. Their cores are so intensely hot and dense, they act as cosmic forges, smashing atoms together to create heavier and heavier elements. Layer by layer, like an onion of nuclear reactions, helium fuses into carbon, carbon into neon, neon into oxygen, and so on, each step releasing enough energy to keep the star from collapsing under its own weight. But the party stops at iron. Iron is the universe's ultimate nuclear dead end. Unlike lighter elements, fusing iron doesn't release energy, it consumes it. So when a blue supergiant's core finally fills with this cosmic ash, the star's fate is sealed. Without outward pressure from fusion to counteract gravity's relentless crush, the core implodes at nearly a quarter the speed of light. The collapse happens so fast that protons and electrons get squeezed together, forming neutrons and unleashing a flood of neutrinos, ghostly particles so abundant. They carry away more energy in 10 seconds than our Sun will emit in its entire lifetime. This implosion triggers a shockwave so powerful, it rips the entire star apart in a type Roman II supernova, an explosion bright enough to outshine entire galaxies. The outer layers, now packed with freshly forged heavy elements like gold, platinum, and uranium, get blasted into space, seeding future generations of stars and planets. But the core, depending on its mass, it either rebounds into a neutron star, a city-sized remnant so dense a teaspoon of it would weigh 1 billion tons, or collapses further into a black hole, vanishing from the visible universe. What makes blue supergiants truly special is their role as cosmic alchemists. Without these short-lived, volatile stars, the universe would lack the heavier elements needed to build planets or life. Every iron atom in your blood, every calcium molecule in your bones, likely passed through the heart of a star like this before being scattered across the cosmos in a supernova's fury. Their existence is a reminder that even in destruction, the universe creates, turning the ashes of dead stars into the building blocks of new worlds. But here's the catch: blue supergiants live fast and die young. While our sun will burn steadily for billions of years, a typical blue supergiant exhausts its fuel in just 10 million, a cosmic blink of an eye. Their brief, brilliant lives end in the most violent explosions known to nature, proving that in the universe, the biggest stars often leave the most spectacular messes behind. And somewhere out there right now, another one is reaching its limit, preparing to light up the cosmos with its dying breath. At the heart of every black hole, where equations break down and infinity looms, there might be an escape hatch from the singularities paradox, a Planck star. This theoretical object dares to suggest that black holes don't end in infinite density, but instead cradle a tiny, ultra-dense remnant no larger than an atom yet containing all the mass of the original star. Picture squeezing the entire Himalaya mountain range into a space smaller than a proton. That's the mind-numbing density we're talking about, where quantum gravity takes over from Einstein's relativity and rewrites the rules of collapse. What stops a Planck star from vanishing into a singularity? The answer lies in the universe's smallest possible scale, the Planck length. At this threshold, space itself becomes grainy, like a digital image zoomed in too far. Instead of collapsing endlessly, matter rebounds in a quantum bounce, like a spring compressed to its absolute limit. The result, a luminous core burning at Planck temperature, a searing 10 to the 32 degrees Kelvin, briefly shining brighter than a galaxy before cooling into darkness. Some models suggest this rebound could even explain certain fast radio bursts, those mysterious cosmic signals that flicker across the universe. The implications are staggering. If Planck stars exist, they'd bridge the gap between quantum mechanics and general relativity, two theories that have stubbornly refused to unite. Inside this quantum fireball, time wouldn't stop as it would at a singularity. It would reverse momentarily during the bounce, a cosmic hiccup in causality. Even wilder, light from the Planck star could escape the black hole's event horizon during this phase, carrying information we thought was lost forever. That means black holes might not be the irreversible data shredders we once believed, but temporary vaults where matter gets compressed, transformed, and eventually released in some altered form. Detecting these hidden cores isn't impossible. As a Planck star evaporates via Hawking radiation, it might leave behind subtle fingerprints, anomalies in the radiation spectrum, or gravitational wave echoes from the bounce itself. Some physicists speculate that primordial black holes, those hypothetical relics from the Big Bang, could now be dying as Planck stars, their final flashes lighting up the cosmos like quantum firecrackers. Others theorize that colliding black holes might briefly expose their Planck cores during mergers, releasing bursts of energy that defy conventional models. This isn't just about salvaging matter from a black hole's grip. It's about rewriting the life cycle of the universe's most enigmatic objects. Planck stars suggest that even in the face of infinite collapse, the universe has a quantum trick up its sleeve, turning the ultimate end into a new kind of beginning. Whether they're real or not, their very possibility proves how much we still have to learn about the extremes of density and how the cosmos might refuse to play by the rules we've written for it. Those beautiful spiral arms stretching across galaxies like cosmic pinwheels aren't solid structures, they're dynamic density waves, rolling through galactic disks like stellar traffic jams. Imagine a highway where cars temporarily bunch up not because the road narrows, but because an invisible wave of slowed movement travels through the traffic. That's exactly how spiral arms work, with stars and gas compressing as they enter these gravitational ripple zones, triggering spectacular bursts of star formation before flowing out the other side. The magic happens because a galaxy's disk doesn't rotate as a single rigid plate. Inner regions whip around faster than the outer ones. As stars and gas clouds orbit, they periodically encounter these slow-moving gravitational waves which act like cosmic speed bumps. When interstellar gas piles up in these regions, the increased pressure ignites the birth of massive new stars. The brightest blue giants you see tracing spiral arms are essentially traffic flares, short-lived stellar newborns that illuminate these temporary congestion zones before racing ahead in their orbits. Here's the twist: individual stars aren't permanently stuck in spiral arms. Our own sun has likely passed through multiple arms during its 4.6 billion-year lifetime, each time experiencing a temporary density spike. This explains why spiral patterns persist for billions of years despite the galaxy's differential rotation. The wave pattern maintains itself while the actual stars flow through it. The arms we see today are just the current snapshot of an ever-changing gravitational dance. Some galaxies take this phenomenon to extremes. The Whirlpool galaxy's dramatic spiral structure is actually being amplified by a smaller companion galaxy tugging on its disk, creating enhanced density waves that spark furious star formation. Other galaxies exhibit flocculent spirals, patchy, cotton-like arms where the density waves are weaker and less organized. These variations prove that while the underlying physics is universal, the visible results depend on a galaxy's mass, gas content, and cosmic environment. What's truly mind-bending is how these waves sculpt galactic ecosystems. As gas clouds compress in spiral arms, they not only create stars but also forge the heavier elements that will someday form planets. The waves even influence where habitable zones might exist too close to the arms, and planetary systems face frequent supernova from all those massive stars too far, and they might lack sufficient heavy elements for rocky worlds. Our solar system's current position between spiral arms might be one reason Earth had a relatively peaceful environment for life to evolve. These self-perpetuating density waves are proof that the universe loves patterns even in chaos. It finds ways to create temporary order. From triggering stellar nurseries to potentially influencing the rise of life, these rhythmic galactic undulations show how density, even when fleeting, can shape the cosmos on the grandest scales. On the surface of a neutron star, even the tiniest imperfections become mountains not of rock, but of pure nuclear matter compressed beyond recognition. These cosmic bumps might stand just millimeters tall, barely noticeable to the naked eye, yet each one carries the weight of Mount Everest multiplied by 1,000,000. That's the surreal physics of neutron star terrain, where gravity's grip is so overpowering, it twists space-time into submission, turning microscopic wrinkles into planetary-scale masses. How does something so small weigh so much? It's all about density. A neutron star's crust is a lattice of atomic nuclei packed shoulder to shoulder in a crystalline structure harder than diamond. In ordinary matter, atoms are mostly empty space electrons whirling far from their nuclei. But here, gravity smashes that emptiness away. The nuclei get squeezed so tightly, they form a solid mat of pure neutrons stacked like marbles in a jar with zero gaps. A sugar cube of this material would outweigh a skyscraper, so when that density gets pinched upward by even a fraction of a millimeter, the result is a mountain with mass beyond earthly comprehension. These minuscule peaks aren't static. Neutron stars spin blisteringly fast, some completing hundreds of rotations every second, and that motion stretches their crusts, creating tiny deformations. Magnetic fields add to the strain, twisting the surface like taffy until microscopic ridges form. The wildest part, these mountains might constantly shift and settle under the star's insane gravity, triggering starquakes that release energy equivalent to hundreds of nuclear bombs, all from a surface ripple no taller than a grain of sand. What stops these mountains from growing taller? Neutron star crusts have a breaking point. Push a deformation beyond a few millimeters, and the crystalline lattice shatters under its own weight, collapsing back into smoothness like a wave crashing onto shore. Some models suggest the tallest possible neutron star mountain might only reach about 10 centimeters, but even at that height, it'd weigh more than all the skyscrapers on Earth combined. These bizarre landscapes aren't just curiosities, they're cosmic laboratories. By studying how neutron star surfaces warp, scientists can probe the limits of material strength under conditions impossible to replicate on Earth. Some researchers even hunt for gravitational waves emitted by these shifting mountains, subtle ripples in space-time that could reveal secrets about the star's internal structure. It's a reminder that in the universe's most extreme environments, even the smallest features defy intuition, reshaping our understanding of what matter can do when pushed to the brink. Black holes might seem like eternal cosmic prisons, but even these gravitational monsters have an expiration date courtesy of a bizarre quantum quirk called Hawking radiation. Picture a black hole's event horizon, the point of no return where gravity's grip is so strong, not even light can escape. According to classical physics, nothing should ever leave. But the universe has a loophole. At the quantum level, space isn't empty, it's a seething foam of virtual particles, constantly popping into and out of existence. Normally, these particle pairs annihilate almost instantly, but near a black hole's horizon, something extraordinary happens. One particle falls in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over time, this slow leak adds up, causing the black hole to lose mass and shrink. The smaller the black hole gets, the faster it evaporates. A stellar mass black hole might take longer than the current age of the universe to vanish, but a tiny, primordial one could explode in a spectacular burst of gamma rays in the blink of a cosmic eye. That final moment, when the black hole's remaining mass converts entirely into energy, would unleash a flash brighter than a supernova, packing all that leftover density into one catastrophic farewell. What's truly mind-bending is how this process flips our intuition about density. As the black hole loses mass, its density increases because the remaining matter is crammed into an ever-shrinking volume. A black hole the size of an atom near the end of its life would be denser than neutron star material, a paradoxical last stand before winking out of existence. Hawking radiation isn't just theoretical. It's the universe's way of balancing the books, ensuring even the darkest objects don't get to keep their plunder forever. And if we ever detect the telltale signature of an evaporating black hole, a sharp, high-energy burst with no obvious source, it'll be proof that even the mightiest cosmic giants must eventually bow to the rules of quantum mechanics. Out in the vast emptiness of space, scientists are creating pockets of matter so cold and still, they defy everything we know about the natural world. These are Bose-Einstein condensates, a bizarre state of matter where atoms stop behaving like individual particles and merge into a single quantum wave, a superatom dancing to the universe's strangest rhythms. To achieve this, researchers use space-based labs like the Cold Atom Lab aboard the International Space Station, where microgravity lets them chill clouds of atoms to within a whisper of absolute zero, colder than the void between galaxies. Here, far from Earth's jostling gravity, atoms slow to a crawl, their quantum properties magnified to scales we can observe and manipulate. What makes these ultra-cold clouds so extraordinary is how they mirror the extreme conditions of cosmic phenomena we can't yet recreate in labs. Neutron stars, black hole event horizons, even the primordial soup of the Big Bang, all involve matter pushed to quantum extremes. By studying condensates, we catch glimpses of how particles might behave in these alien environments. Take quantum tunneling, for example. In a Bose-Einstein condensate, atoms can teleport through barriers as if they were ghosts, a phenomenon that might explain how particles escape a black hole's grip or traverse the quantum foam of spacetime. The condensates themselves are eerily beautiful. Picture a gas so cold it forms glowing, undulating blobs that obey the laws of fluid dynamics and quantum mechanics simultaneously. These blobs can flow without friction, climb walls against gravity, and even freeze into crystalline patterns of pure light. In space, freed from Earth's gravity, they expand to sizes impossible in terrestrial labs, revealing quantum behaviors hidden on our planet. Some experiments have created atom lasers, coherent beams of matter that could one day help us probe the fabric of space-time with unprecedented precision. But the real magic lies in what these experiments suggest about the universe. Superconductors, neutron star superfluids, even dark matter's elusive properties might share kinship with these ultra-cold quantum states. By mastering Bose-Einstein condensates in orbit, we're not just doing physics, we're building bridges between the quantum and the cosmic, one frozen atom at a time. And who knows, the key to unlocking the universe's densest mysteries might not lie in a telescope's lens, but in a cloud of atoms colder than deep space itself. While black holes and neutron stars pull with gravity's irresistible grip, the cosmos harbors a shadowy counterforce, dark energy, an invisible presence pushing space itself apart at an ever-accelerating pace. Picture the universe as a cosmic tug-of-war. On one side, dense matter clumps together, collapsing into galaxies and clusters under gravity's relentless crush. On the other, dark energy stretches the very fabric of spacetime, driving galaxies apart so fiercely that one day, even the closest neighbors could vanish beyond an unreachable horizon. This isn't just theoretical. Dark energy makes up 68% of the universe's total energy budget, outweighing both matter and dark matter combined. Its repulsive force behaves like an anti-gravity agent, but with a chilling twist. It doesn't weaken as space expands. Unlike gravity, which fades with distance, dark energy grows stronger as the universe stretches, creating more space to fuel its expansion. The result, a future where galaxy clusters grow isolated, their light stretched into invisibility, and new stars cease to form as cosmic structures are torn apart. Yet the battle isn't one-sided. In regions where matter is densest, like galaxy clusters, gravity still holds sway, creating localized pockets where dark energy's influence is temporarily held at bay. These clusters become cosmic fortresses, their immense mass bending spacetime enough to resist the void's outward rush. But even their defiance has an expiration date. Over trillions of years, as dark energies push overwhelms gravity's pull, these clusters too will dissolve, their stars fading into darkness as the universe cools toward an icy, desolate end. The irony is profound. The same dense objects we marvel at, black holes, neutron stars, even the supermassive giants anchoring galaxies, are ultimately at the mercy of this elusive, all-pervasive energy. Dark energy doesn't just shape the universe's fate, it rewrites the rules, proving that in the grand scheme, density is fleeting. The cosmic voids between galaxies, once thought empty, are the true battlegrounds where this invisible force is winning. What's perhaps most haunting is the timing. Dark energy's dominance began roughly 5 billion years ago, coinciding with our solar system's formation. We exist in a brief window where both forces are observable, where galaxies still shine and cosmic structures remain intact. Future civilizations, should they arise, might gaze into a vastly emptier sky, their telescopes revealing none of the grandeur we see today. The universe's densest wonders are temporary, outshone, in the end, by the boundless, silent push of nothingness itself. Brown dwarfs are cosmic in-betweeners, objects too massive to be planets yet too puny to shine like true stars. Stuck in stellar limbo, these failed stars never quite muster the core pressure needed for sustained hydrogen fusion, the process that powers stars like our Sun. Yet inside their dim, cool bodies lurks a secret, cores of metallic hydrogen, a bizarre state of matter so extreme, it defies ordinary chemistry. Imagine a sphere of gas dozens of times more massive than Jupiter, collapsing under its own gravity until something strange happens. At around 1 million times Earth's atmospheric pressure, hydrogen, normally a transparent, lightweight gas, undergoes a radical transformation. Its electrons break free from their atomic orbits, forming a soup of nuclei swimming in a sea of delocalized electrons. This isn't just dense matter, it's a quantum-scale metal capable of conducting electricity like copper while remaining a fluid. The result? A brown dwarf's heart behaves like a giant celestial circuit board, its churning metallic layers generating magnetic fields thousands of times stronger than Jupiter's. What makes these cores especially peculiar is how they blur planetary and stellar physics. In stars, convection carries heat outward in roiling currents, but in brown dwarfs, metallic hydrogen's conductivity dominates, creating a thermal traffic jam where energy struggles to escape. That's why many brown dwarfs glow faintly in infrared, not from fusion, but from residual heat slowly leaking from their pressurized cores. Over billions of years, they cool into increasingly dim orbs, their metallic hearts gradually solidifying into exotic crystalline forms unseen anywhere else in the universe. The line between planet and brown dwarf gets even fuzzier when you consider their weather. Those metallic interiors likely drive vicious storms, with clouds of molten sand and raindrops of liquid metal swirling in atmospheres hotter than a blast furnace. Some brown dwarfs even exhibit auroras, their powerful magnetic fields channeling charged particles into eerie light shows without a host star's solar wind to power them. Yet for all their strangeness, brown dwarfs might be cosmic heavyweights in disguise. Theories suggest they could outnumber regular stars in our galaxy, lurking unseen in the dark. Some may even harbor rogue planets in orbit, their dense cores anchoring miniature solar systems with no sun. And when two brown dwarfs collide, the result might be a sudden, short-lived stellar ignition, a flicker of true stardom before fading back into the dark. These misfits of the cosmos challenge our definitions of stars and planets, proving that nature doesn't care for tidy categories. In their hearts, the universe explores states of matter impossible to recreate on Earth, reminding us that sometimes the most fascinating objects are the ones that never quite made the cut. The crust of a neutron star is no ordinary surface. It's a solid shell of neutron-rich material 10 billion times stronger than steel, forged under pressures that turn atomic nuclei into a crystalline lattice. Yet even this near-indestructible armor has its breaking point. When gravitational forces or twisting magnetic fields stress this ultra-dense crust beyond its limit, the entire star shudders violently in what astronomers call a starquake, a seismic event that makes our planet's most devastating earthquakes look like gentle tremors by comparison. During these cosmic convulsions, the crust fractures and rebounds, releasing pent-up energy equivalent to hundreds of millions of hydrogen bombs in milliseconds. The sheer scale is staggering. A single neutron starquake can unleash more energy than our Sun emits in 100,000 years. Most of this fury comes from the crust's unimaginable stiffness. Picture cracking a diamond the size of Manhattan, then watching the shockwaves ripple through material denser than an atomic nucleus. The fractures themselves are microscopic by cosmic standards, mere centimeters tall, but because the crustal material weighs 1 billion tons per teaspoon, even these tiny ruptures unleash apocalyptic forces. What triggers these spectacular events? Many originate from the star's absurdly powerful magnetic fields, which can grow stronger than any laboratory magnet by a factor of 1 trillion. These fields don't just surround the star, they're frozen into its crust during formation, creating internal stresses as the star gradually slows its rotation. When the crust finally snaps under this magnetic strain, it realigns like tectonic plates on steroids, emitting bursts of X-rays and gamma rays detectable across interstellar distances. Some neutron stars exhibit glitches, sudden speed-ups in rotation that scientists now believe are caused by starquakes abruptly changing the star's moment of inertia. The aftermath resembles a cosmic crime scene. The quakes leave behind mountains on the neutron star's surface, deformations just millimeters high, yet containing more mass than all Earth's mountains combined. More dramatically, they sometimes generate magnetar flares, sudden, terrifyingly bright eruptions where the star's magnetic field reconnects, releasing enough energy in 1/10 of a second to outshine 100,000 suns. In 2004, a starquake on magnetar SGR 1800620 created a gamma-ray pulse so powerful it temporarily ionized Earth's upper atmosphere from 50,000 light-years away, despite being halfway across the galaxy. These events aren't just spectacular, they're cosmic laboratories. By studying starquake vibrations, astronomers probe the neutron star's internal structure like geologists use earthquakes to map Earth's core. The waves travel at nearly light speed through the star's hyper-dense interior, revealing whether the core contains exotic states like superfluids or free quarks. Some theorists even suggest certain gravitational wave detections could be the fingerprints of especially massive starquakes, where the entire star rings like a bell from crust to core. What's most humbling is how these unimaginably violent events unfold on objects smaller than many cities. A neutron starquake represents matter pushed so far beyond earthly limits that our usual definitions of solid and rigid lose all meaning, where a crack no wider than a coin can alter the course of an entire star's evolution. In these fleeting moments of rupture, we catch glimpses of physics operating where no laboratory will ever reach, and where the universe tests the absolute limits of material strength. Gamma-ray bursts are the universe's brightest flashbulbs, cosmic explosions so intense they can outshine 1,000,000 trillion suns in mere seconds. These monumental blasts occur when the most massive stars exhaust their nuclear fuel and collapse, not with a whimper, but with a scream of energy that pierces the cosmos. But what makes them truly extraordinary isn't just their staggering luminosity. It's the unfathomable density packed into their relativistic jets, narrow beams of plasma and radiation that blast outward at over 99% the speed of light. At the heart of a gamma-ray burst lies a dying star's final act. As the core implodes, it doesn't just form a neutron star or black hole. It triggers a cataclysmic engine that channels the star's remaining energy into twin jets, focused like cosmic blowtorches. These jets are so tightly collimated, their energy isn't wasted in all directions. It's concentrated into beams no wider than a few degrees. The result: a burst packing more energy into a few seconds than our Sun will emit in its entire 10-billion-year lifespan. The numbers defy intuition. Within these jets, matter is accelerated to such extreme velocities that particles smash into one another with enough force to create gamma rays, the most energetic form of light. Meanwhile, the jet's internal density soars beyond anything found in neutron stars or even black hole accretion disks. A single cubic centimeter of this plasma could contain enough kinetic energy to power human civilization for millennia. And because these jets move so close to light speed, their radiation is squeezed into an even narrower cone by relativistic effects, amplifying their apparent brightness to mind-bending levels. What's wild is how fleeting they are. The initial gamma-ray flash might last only 2 seconds or stretch to a few minutes, but its afterglow, created as the jet plows into surrounding gas, can linger for days or weeks, fading across the electromagnetic spectrum from X-rays to radio waves. Some bursts, like GRB 1222 in 2012, released more energy in 1 minute than the Sun will in its entire lifetime. And because gamma rays travel unimpeded across cosmic distances, these events serve as lighthouses visible clear across the observable universe, their light older than the Earth itself. But the real mystery lies in what powers them. While most gamma-ray bursts stem from collapsing massive stars, others might originate from neutron star collisions, where the resulting kilonova flings out jets of neutron-rich debris. The exact mechanism behind these beams, whether magnetic fields, neutrino annihilation, or some other exotic physics, remains hotly debated. What's certain is that their existence challenges our understanding of extreme astrophysics, proving that even in death, stars can unleash forces beyond anything we've witnessed elsewhere in the cosmos. Detecting these bursts is like catching a cosmic lightning strike. Satellites like Swift and Fermi scan the skies around the clock, waiting for the telltale flash of high-energy photons that signal a burst's arrival. When one is spotted, telescopes worldwide swivel to catch the afterglow, piecing together clues about the explosion's origins and the distant galaxy that birthed it. Some bursts even come with gravitational wave counterparts, offering a multi-messenger glimpse into the universe's most violent events. Gamma-ray bursts are more than just dazzling fireworks, they're probes of the early universe. The most distant bursts yet detected emitted their light when the cosmos was just a fraction of its current age, making them time capsules from an era when galaxies were first forming. Their light, stretched by cosmic expansion, carries fingerprints of the gas and dust it traversed, revealing the composition of ancient space. And because they're so bright, they illuminate everything in their path, from intervening galaxies to the intergalactic medium itself. Yet for all their brilliance, gamma-ray bursts also pose a sobering thought experiment. If one occurred too close to Earth within a few thousand light years, its radiation could strip our ozone layer, triggering mass extinctions. Thankfully, the nearest candidates are far enough away to pose no threat. Instead, they serve as cosmic reminders of the universe's raw power, proof that even in the vast quiet of space, density and velocity can conspire to create flashes of violence that outshine galaxies. If black holes are the universe's ultimate one-way streets, white holes might be their cosmic ejector seats, theoretical exits where matter blasts outward from infinite density rather than vanishing forever. These bizarre objects, first proposed as mathematical solutions to Einstein's equations of general relativity, flip the script on everything we know about gravitational extremes. Picture a black hole in reverse. Instead of an event horizon that traps all incoming matter, a white hole would have a boundary that forbids anything from entering, violently spewing light, gas, and particles into space like a cosmic geyser with no off switch. The origins of white holes are just as mind-bending as their behavior. Some theories suggest they could be the other end of black holes, connected by bridges through space-time called wormholes. In this scenario, matter swallowed by a black hole in one corner of the universe might get spat out through a white hole elsewhere, or even in another universe entirely. Others propose white holes as remnants of a black hole's death, throws after evaporating via Hawking radiation, a final rebound where all that trapped energy erupts back into existence. The most radical idea, that the Big Bang itself was a white hole event with our entire universe bursting forth from an infinitely dense singularity. What makes white holes especially tantalizing is their potential to solve one of physics' biggest headaches, the black hole information paradox. If black holes permanently destroy information about the matter they consume, it violates quantum mechanics' rule that information can never be lost. White holes could preserve that data by recycling it back into the cosmos, like a cosmic photocopier that never jams. The catch, we've never observed one. Their theoretical nature makes them frustratingly elusive if they exist at all. The challenges of detecting white holes are monumental. Unlike black holes, which reveal themselves by devouring nearby stars or glowing in X-rays as they rip gas to shreds, white holes would be far more fleeting. Their outbursts might resemble gamma-ray bursts or quasars, but with no visible engine to explain them. Some astronomers have speculated that certain unexplained high-energy cosmic rays or fast radio bursts could be white hole signatures, though no smoking gun has emerged. There's also the issue of stability. Mathematical models suggest white holes would collapse into black holes almost instantly unless propped up by exotic physics, like negative energy or quantum gravity effects. Yet the mere possibility of white holes forces us to rethink the universe's most extreme environments. If they're real, they'd rewrite the rules of cause and effect, showing that density doesn't always lead to collapse. Sometimes it might trigger a cosmic rebirth. They're a reminder that for every rule the universe seems to follow, there might be an exception lurking in the math waiting to be discovered. And if we ever spot one, it wouldn't just confirm a wild theory. It would open a portal to understanding how space-time, matter, and the arrow of time itself might work in ways we've yet to imagine. Most stars have vast, roiling atmospheres, but not neutron stars. These ultra-dense remnants pack their entire visible outer layer into a wispy shell just centimeters thick, so tenuous you could fly a spacecraft through it without noticing. If you somehow survived the crushing gravity and deadly radiation, yet despite being thinner than a bedsheet draped over Manhattan, this atmosphere is still denser than Earth's entire crust. How? Because neutron stars don't play by normal rules. Their incomprehensible gravity compresses even trace gases into something resembling solid metal. Picture Earth's atmosphere, a fluffy blanket of nitrogen and oxygen stretching 50 miles high, weighing about 5 quadrillion tons total. Now imagine taking all that air and crushing it into a layer thinner than your fingernail. That's the neutron star's version of thin. The few atoms clinging to its surface get pressed into a degenerate quantum state, stacking like sardines in a can where electrons can't even orbit nuclei normally. Oxygen, carbon, or iron atoms, whatever sparse elements survived the star's collapse, get flattened into two-dimensional sheets, their electron clouds warped into bizarre shapes by magnetic fields a trillion times stronger than Earth. What's astonishing isn't just the atmosphere's density, but its heat. While Earth's crust averages a chilly 15 degrees Celsius, a neutron star's gaseous veneer burns at nearly 1,000,000 degrees. That thermal energy actually helps the atmosphere cling to the surface against gravity's pull. Atoms get so agitated, they resist being fully swallowed. Some models suggest this layer might even sparkle with nuclear fusion at its base, as stray hydrogen atoms crushed together ignite in microscopic firecrawls. The true oddity lies in how this atmosphere interacts with the star's surface. Below it lies the neutron star's solid crust, a crystalline lattice of pure neutrons harder than diamond. Where these two layers meet, conditions grow so extreme that atoms dissolve entirely, their electrons merging with protons to form more neutrons in a process called electron capture. This creates a surreal boundary, an ocean of degenerate gas floating seamlessly atop a sea of neutron-rich ice, with no distinct transition between them. Yet this wispy shroud holds cosmic significance. When neutron stars accrete gas from companion stars, their atmospheres become blast furnaces, heating incoming material until it emits X-rays bright enough to spot across galaxies. Some pulsars even burp their atmospheres during starquakes, ejecting globs of ultra-dense plasma that cool into floating metal clouds. And because these thin layers filter the radiation pouring from the star's surface, studying their absorption lines gives astronomers an indirect way to probe the exotic physics below, like deciphering a distant fire by the shadows cast in its smoke. For an object born in stellar catastrophe, it's poetic that even its faintest breath defies earthly logic. The neutron star's atmosphere proves density isn't about quantity. It's about how the universe redistributes what little remains when matter gets pushed past the brink of imagination. Just outside a black hole's event horizon lies one of the most mind-bending regions in the universe, a place where light itself gets trapped in an endless cosmic waltz. This is the photon sphere, a razor-thin orbit where space-time curves so severely that photons, the particles of light, circle the black hole like cars on a racetrack with no exit. Imagine a beam of light traveling at 300,000 kilometers per second, suddenly caught in a gravitational grip so strong it bends back on itself, forced to loop around the void forever unless disturbed. The physics behind this is as elegant as it is terrifying. At precisely 1.5 times the Schwarzschild radius, the black hole's point of no-return spacetime curvature reaches a perfect balance. Here, photons don't plunge inward or escape outward. They follow a circular path called a null geodesic, a trajectory where space twists so tightly that even light's straight-line motion becomes a closed loop. It's like trying to walk a straight line on a trampoline with a bowling ball at the center. Your path inevitably curves back to where you started, but this delicate dance is unstable. The slightest nudge, say, a stray particle collision or gravitational ripple, can fling photons either into the black hole's abyss or out into the universe. That's why we don't see perfect rings of light hovering around black holes. Instead, the photon sphere reveals itself indirectly. When we peer at images like the one from the Event Horizon Telescope, the bright halo surrounding the black hole's shadow is partly fueled by light skimming this critical orbit, photons that looped once or twice before breaking free to reach our telescopes. The strangest part, for an observer hovering near the photon sphere, time would warp to absurd extremes. Watch a photon complete its circular orbit, and you'd see it take mere microseconds. But to someone far away, that same photon might appear frozen in place, its image stretched and redshifted by the black hole's gravity. This bizarre time dilation means the photon sphere isn't just a spatial boundary, it's a hall of mirrors where light's behavior defies intuition. Some black holes take this illusion further. Spin a black hole fast enough, and its photon sphere fractures into multiple layers like nested Russian dolls of light. Kerr black holes, the type formed from rotating stars, can have photon spheres tilted at angles or even shaped like warped donuts, their paths twisted by the black hole's drag on spacetime itself. These variations aren't just mathematical curiosities. They're clues about the black hole's spin, mass, and the violent history that shaped it. What's truly humbling is how photon spheres expose the universe's knack for turning physics into art. They're cosmic prisons for light, yes, but also natural lenses, bending and amplifying starlight in ways that let astronomers probe distant galaxies. They're proof that even in the darkest corners of existence, the universe finds ways to play with the very fabric of reality, leaving trails of trapped light as breadcrumbs for us to follow. The cosmic web is the universe's grandest architectural masterpiece, not built of steel or stone, but spun from invisible dark matter and traced by glittering galaxies. This vast, intricate network stretches across billions of light years, with galaxies huddled along dense filaments like beads on a string, separated by unimaginably empty voids. What's staggering isn't just its scale, but its density contrasts. Those dark matter threads, though nearly invisible, contain enough mass to bend spacetime itself, while the voids between them are so empty, a single atom might drift for millions of years without collision. These filaments aren't random. They're relics of the early universe, when tiny quantum fluctuations in the primordial soup of the Big Bang grew under gravity's pull, amplifying into a web-like scaffold. Dark matter, the universe's hidden skeleton, clumped first, its gravity funneling ordinary gas and dust into dense knots where galaxies eventually ignited. Picture it like a cosmic watershed. Dark matter's gravity forms the valleys, and galaxies flow into them like rivers pooling in lowlands. The result: a sponge-like structure where over half of all galaxies reside in just 1% of the universe's volume, leaving the rest as near-perfect nothingness. The numbers defy intuition. A typical filament might be 50 million light-years long, but only 5 million light-years wide, with a density 10 to 20 times the cosmic average. Yet even that pales next to the nodes where filaments intersect galaxy clusters so packed. They contain thousands of galaxies orbiting a common center, bound by dark matter's vice-like grip. Meanwhile, the voids between filaments can be 100 times emptier than the filaments themselves, with densities closer to intergalactic space than to any recognizable structure. How do we map something so ethereal? Astronomers use galaxies as cosmic breadcrumbs, tracing their distribution across the sky to reveal the web's hidden geometry. But the real detective work involves gravitational lensing, the way dark matter's mass warps light from background objects, betraying its presence like fingerprints on glass. Simulations supercharge this effort, recreating the web's evolution from the Big Bang to today, showing how dark matter's subtle tug sculpted everything we see. The cosmic web isn't static, it's a living, breathing structure. Filaments funnel gas into galaxy clusters, fueling new star birth, while voids expand relentlessly, pushing galaxies further apart. In the distant future, as dark energy accelerates the universe's expansion, those filaments may stretch to breaking, isolating galaxies in an ever-darkening cosmos. But for now, they stand as a testament to density's power, proof that even in the grandest scales, the universe weaves order from chaos, one invisible thread at a time. Magnetars don't just possess the strongest magnetic fields in the universe, they wield them like cosmic weapons, twisting space-time itself until it snaps. These neutron star variants generate fields so intense, they could strip the electrons from your atoms from halfway across the Milky Way. But unlike the steady pull of ordinary magnets, a magnetar's power is fleeting. Over centuries, their apocalyptic magnetic fields decay, unleashing energy in violent spasms that light up the cosmos like celestial grenades. The process begins deep inside the star's superfluid core, where protons and electrons swirl in a quantum dance. As the star's rotation slows, this churning sea of charged particles gradually loses energy, causing the magnetic field, threaded through the star like invisible wires, to weaken. But here's the twist: the field doesn't fade quietly. It fractures, its lines tangling and reconnecting in explosive bursts that rip through the magnetar's ironclad crust. Imagine a rubber band stretched to its limit, then multiply that tension by a quadrillion. That's the kind of stress building beneath the surface before a catastrophic magnetic rearrangement. When the breaking point arrives, the results are spectacular. The crust shudders in a starquake, cracking like a diamond anvil under a hammer. This releases pent-up magnetic energy in the form of X-ray flares so bright, they temporarily outshine every other source in the galaxy. In 2004, magnetar SGR 18620 emitted a flare equivalent to 50,000 years of the Sun's output in just a tenth of a second. The burst was so powerful, it bounced off the Moon and ionized Earth's upper atmosphere from 50,000 light-years away, like a lightning strike felt across continents. What's terrifying is how unpredictable these eruptions are. Unlike pulsars, which tick with metronomic precision, magnetars lurk in silence until their magnetic tantrums strike without warning. Some theorists suggest these outbursts might involve magnetic bubbles, regions where the field coils back on itself like a twisted telephone cord before violently snapping straight. Others propose the flares stem from twisted magnetospheres, where magnetic field lines knot themselves into Gordian loops before slicing apart in bursts of particle acceleration. Yet these dying magnetic fields aren't just agents of chaos, they're cosmic gold mines for astrophysicists. Each flare carries fingerprints of the magnetar's internal structure, revealing details about the neutron star's crustal rigidity, core composition, and even the nature of spacetime near its surface. Some X-ray pulses show bizarre oscillations, hinting at starquakes reverberating through the magnetar's crystalline crust. Others exhibit spectral lines warped by quantum electrodynamics, a rare glimpse of physics operating under conditions no lab could ever replicate. The ultimate fate of a magnetar is a slow fade into obscurity. As its magnetic field bleeds away over millennia, the star's violent outbursts grow rarer, leaving behind an ordinary neutron star still dense, still strange, but no longer a magnetic monster. Yet in their twilight, these objects leave behind a lingering mystery. Their remnants might explain anomalous X-ray pulsars, a class of neutron stars too luminous to be powered by rotation alone. Perhaps these are magnetars in their final act, their decaying fields still hot enough to glow in X-rays long after their explosive youth has passed. Magnetar flares are more than just cosmic fireworks, they're reminders that even the universe's most extreme objects are temporary. What seems invincible today, whether a star's magnetic grip or the laws we think govern it may already be unraveling in ways we're only beginning to understand. And somewhere out there, another magnetar's field is fraying at the edges, preparing to remind the cosmos that nothing, not even space-time's fiercest distortions, lasts forever. Quantum black holes sound like science fiction tiny, atom-sized singularities popping into existence in particle colliders before vanishing in a puff of radiation. Yet these microscopic monsters aren't just theoretical fantasies. They're potential byproducts of the universe's most extreme physics experiments. When particle accelerators like the Large Hadron Collider smash protons together at near-light speeds, they recreate conditions not seen since the Big Bang's first trillionth of a second. Under those energies, space-time itself could wrinkle into microscopic black holes a billion times smaller than an atom, lasting only fractions of a nanosecond before evaporating in a flash of Hawking radiation. How could something so small even form? It all hinges on extra dimensions, a wild idea from string theory suggesting our universe might have more than the three spatial dimensions we experience. If these hidden dimensions exist, gravity could become exponentially stronger at tiny scales, allowing enough energy to collapse into a quantum black hole during particle collisions. Picture 2 grains of sand colliding with such force that they briefly crush themselves into a black hole the size of a single proton. The math suggests these would be harmless, evaporating instantly, but their fleeting existence would shatter our understanding of quantum gravity. The real magic lies in their evaporation. Thanks to Hawking radiation, quantum black holes wouldn't have time to gobble up matter. Instead, they'd emit their entire mass as energy almost immediately, leaving behind only a faint burst of particles. Detecting this signature is like trying to spot a firefly's glow in a fireworks display, nearly impossible amid the chaos of particle collisions. Yet some experiments hunt for unusual energy patterns or missing momentum in collision debris that might betray a black hole's birth and death. What's mind-bending is the scale. A quantum black hole packing the mass of Mount Everest into a space smaller than a quark would have a temperature of trillions of degrees, hotter than any supernova. Its evaporation would release energy equivalent to a nuclear bomb, but confined to a volume so tiny, it wouldn't even scorch a single cell in your body. These paradoxes make quantum black holes perfect laboratories for testing the union of relativity and quantum mechanics, 2 theories that famously refuse to play nice. The hunt for them isn't just academic. If discovered, they'd prove extra dimensions exist, revolutionize our grasp of gravity, and maybe even unlock the secrets of the universe's birth. And if they're never found, that absence would force physicists back to the drawing board, proving once again that the universe guards its most extreme secrets fiercely. Either way, the mere possibility shows how far we'll go to test the limits of reality, one tiny, self-destructing singularity at a time. At the heart of every pulsar lies a cosmic lighthouse, spinning so fast it blurs the boundary between physics and magic. These neutron star remnants don't just rotate, they pirouette with such precision. Their beams of radiation sweep across space like celestial searchlights, flashing with metronomic regularity. The secret behind this mesmerizing display is an extreme density engine operating under conditions that warp the very laws of electromagnetism. Picture a neutron star's core, a superfluid soup of neutrons spinning effortlessly at hundreds of revolutions per second. But it's the star's crust that takes this chaos and channels it into breathtaking order. As the star rotates, its unimaginably strong magnetic field, trillions of times more powerful than Earth's, transforms into a colossal particle accelerator. Charged particles get whipped along magnetic field lines, streaming from the magnetic poles at near light speed. When these particles slam into the surrounding plasma near the star's surface, they emit focused beams of radio waves, X-rays, and gamma rays in narrow cones. The precision of these beams defies belief. Some pulsars, like the famous crab pulsar, fire radiation pulses every 33 milliseconds, so regular they rival atomic clocks. Others, called millisecond pulsars, spin over 700 times per second, their beams stitching intricate patterns across the cosmos. What keeps this cosmic strobe light perfectly timed is the neutron star's incredible density. Its moment of inertia so immense that even the slightest wobble gets corrected instantly, like a gyroscope the size of Manhattan maintaining perfect balance. But pulsar cores have even wilder tricks. Some models suggest their interiors might contain exotic states of matter-free quarks or hyperons that enhance the magnetic dynamo effect. Others propose glitches, sudden speed-ups in rotation, occur when the superfluid core momentarily decouples from the crust, releasing pent-up energy like a wound spring snapping back into place. These events can alter the pulsar's beam pattern subtly, giving astronomers clues about the star's internal structure. The beams themselves are anything but simple flashlights. As radiation climbs out of the pulsar's intense gravitational field, it undergoes relativistic beaming, an effect where light gets focused into an increasingly narrow cone by the star's rapid spin. This creates bizarre visibility zones where distant observers might see multiple pulses per rotation or detect the pulsar only during precise alignment windows. Some pulsars even exhibit nulling, periods when their beams mysteriously switch off for minutes to years, possibly due to magnetic field rearrangements deep in their cores. What's truly astonishing is how these dense cores power beams visible across interstellar distances. The Vela pulsar, for instance, radiates enough energy in its beams to light up a small planet, all from a core just 20 kilometers wide. And because pulsars slow down predictably as they age, losing rotational energy to radiation and particle acceleration, their beams serve as cosmic chronometers. By measuring subtle changes in pulse timing, astronomers have detected gravitational waves, mapped interstellar gas, and even tested Einstein's theory of relativity with precision beyond Earth's finest laboratories. These spinning denser than atomic nuclei are more than cosmic curiosities. They're the universe's ultimate precision instruments, turning raw gravitational collapse into perfectly timed signals that illuminate the darkest corners of physics. Every pulse carries encrypted messages about matter pushed beyond its breaking point, reminding us that sometimes the most extreme densities create the most beautiful order. When a dying star's core collapses, it doesn't just quietly fade away. It stages the most spectacular comeback in the universe. As the imploding core reaches neutron star density, a mind-bending reversal occurs. Matter rebounds like a cosmic trampoline, launching a shockwave outward at 15,000 kilometers per second. This isn't just any shockwave, it's nature's ultimate pressure cooker, where elements get forged under conditions so extreme, they make a hydrogen bomb look like a birthday candle. The shockwave's destructive power hides a creative secret. As it tears through the star's outer layers, temperatures soar beyond 5 billion degrees, hot enough to rip atomic nuclei apart and reassemble them into heavier elements through rapid neutron capture. Here, in this fleeting inferno, iron nuclei, the star's original ash, get bombarded with so many free neutrons that they balloon into unstable isotopes of gold, platinum, and even uranium within seconds. This is how the universe builds its heaviest elements, not in the star's lifetime of steady fusion, but in its final explosive death throes. What makes supernova shockwaves so uniquely destructive and creative is their staggering energy gradient. Unlike Earth-bound explosions that fade quickly, these cosmic blasts maintain their intensity across thousands of kilometers of stellar material. The shock front behaves like a runaway snowplow, piling up gas ahead of it until the pressure triggers new fusion reactions. Some models suggest the wave actually reignites nuclear burning in regions that had previously stopped fusing, creating a layered chemical factory that stamps its signature into the ejected debris. The remnants tell this story in vivid detail. When astronomers analyze supernova leftovers like Cassiopeia A, they find telltale mixes of silicon, titanium, and iron group elements arranged in expanding shells, like an onion blasted apart mid-formation. X-ray observations reveal even heavier elements concentrated in specific regions, clues pointing to where the shockwave's most intense neutron fluxes occurred. Some neutron-rich isotopes like nickel-56 decay into iron over time, explaining why the universe's iron abundance keeps growing long after the first stars died. But the real magic happens when the shockwave reaches the star's surface. After plowing through millions of kilometers of dense plasma, the wave finally breaks free, accelerating outer material to relativistic speeds. This is when the supernova becomes visible across the cosmos, a burst of light so brilliant it can outshine entire galaxies. The same shock that forged gold now paints the interstellar medium with those freshly minted elements, seeding future generations of stars and planets with the ingredients for rocky worlds and perhaps even life. What's astonishing is how ephemeral this alchemy is. The entire heavy element production from iron to uranium unfolds in less than a minute before the shockwave dissipates into space. Yet that brief moment leaves an indelible mark on cosmic history. Every gold ring, every uranium atom on Earth traces back to such cataclysms, relics of stellar cores that rebounded with enough force to reshape the periodic table itself. Supernova shockwaves don't just destroy stars, they're the universe's ultimate recyclers, turning stellar death into the building blocks of new beginnings. Getting too close to a neutron star wouldn't just kill you, it would rewrite your body's definition of physical form atom by atom. These cosmic remnants wield gravity so fierce, the difference in pull between your head and feet would stretch you into a human noodle before you even crossed the event horizon. Picture this, your feet, just a few meters closer to the star than your head, would experience a gravitational tug hundreds of millions of times stronger, yanking them downward with the force of 1,000,000 freight trains while your upper body lags behind. The result, spaghettification, a real astrophysical term for the brutal process where gravity's tidal forces turn anything into a stream of particles. But neutron stars take this horror to unprecedented extremes. Unlike black holes where spaghettification happens inside the event horizon, neutron stars don't offer the courtesy of invisibility. You'd see the surface looming as your body stretches muscles, bones, even individual cells torn apart by the star's gravitational gradient. At a distance of about 1,000 kilometers, the tidal forces would already overpower molecular bonds, separating your molecules like beads on a snapped string. By the time you're 100 kilometers away, atomic bonds fail, ripping electrons from nuclei in a gruesome plasma spray. The physics behind this is deceptively simple. Gravity weakens with distance, and neutron stars are so compact that a slight change in proximity means a catastrophic jump in gravitational pull. Stand next to one, and the side of your body facing the star experiences a force exponentially stronger than the opposite side. Earth's gravity stretches our oceans to create tides, but a neutron star's version would turn the moon into a ribbon of molten rock in seconds. What's truly chilling is the timescale. On a black hole, spaghettification might take minutes. On a neutron star, milliseconds. Your nervous system wouldn't have time to register pain before your body disintegrated into a stream of subatomic debris, joining the star's atmosphere as a haze of ionized particles. Even if you somehow survived the stretch, the star's surface, a crystalline crust of pure neutron matter, would vaporize you on impact with the energy of 1,000 nuclear bombs per square centimeter. This isn't just theoretical grimness, it's a window into how matter behaves under extremes we can't replicate on Earth. Neutron stars are the universe's most effective particle accelerators, shredding objects with forces that reveal the limits of atomic cohesion. Every probe or hypothetical astronaut we imagine falling toward one carries back data written in their annihilation. that in the face of such density, not even the fundamental glue of reality holds firm. Outside the event horizon of a spinning black hole lies a cosmic whirlpool so intense, it defies the very concept of stillness, the ergosphere. This warped region of space doesn't just bend the rules of physics, it shreds them. Picture the black hole's rotation twisting space-time like honey stirred by an invisible spoon, creating a zone where not even light can resist being dragged along for the ride. Unlike the event horizon's point of no return, the ergosphere is a bizarre limbo, a place where escape is technically possible, but only if you're moving faster than the speed of light in the opposite direction. What makes the ergosphere so unnerving is its effect on the fabric of reality itself. Within this warped space, the black hole's spin drags space-time along with it, a phenomenon called frame dragging. Imagine standing on a merry-go-round spinning at near light speed, except the floor beneath you isn't just moving. It's the very dimension of space being yanked in circles. Here, standing still becomes impossible. Even if you fire your rocket thrusters at full power to counter the drag, space-time's relentless current will still pull you clockwise around the black hole like a leaf caught in a hurricane. This isn't just theoretical. The ergosphere's existence was confirmed indirectly by NASA's Gravity Probe B, which detected frame dragging around Earth, a minuscule effect compared to the cosmic whirlpool surrounding a Kerr black hole. Near these rotating monsters, the effect is so extreme that particles entering the ergosphere can get slingshotted outward with more energy than they arrived with, a process known as the Penrose mechanism. Essentially, the black hole's spin acts like a cosmic battery, stealing rotational energy and spitting it back out as high-velocity matter. Some theories suggest this could explain the insanely powerful jets seen blasting from active galactic nuclei. The ergosphere's shape is just as bizarre as its physics. Instead of a perfect sphere like the event horizon, it's flattened at the poles and bulging at the equator, resembling a squashed beach ball. This asymmetry comes from the black hole's rotation flinging space-time outward along the plane of spin. At the poles where frame dragging is weakest, the ergosphere nearly touches the event horizon. But at the equator, it stretches far out into space, creating a wider zone of no return for unwary travelers. Here's where it gets even wilder. The ergosphere might be the key to harvesting energy from a black hole. Hypothetical civilizations could, in theory, lower objects into this region on tethers. As space-time drags the object along, the tether would twist, generating usable energy like a water wheel in a river of twisted dimensions. Of course, the engineering challenges are beyond anything we can imagine, but the principle reveals how black holes aren't just cosmic vacuum cleaners, they're dynamos of distorted space-time, offering glimpses into physics we've yet to fully understand. The ergosphere stands as one of the universe's most striking examples of how extreme density and motion can reshape reality. It's a place where the simple act of trying to stay still becomes a battle against the fabric of the cosmos itself, and where the universe reminds us that in the presence of such titanic forces, even the laws of motion are merely suggestions. The early universe was no serene cosmic cradle. It was a seething, ultra-dense maelstrom where the entire observable cosmos packed into a volume smaller than a single atom. 1 second after the Big Bang, the universe's density skyrocketed to over 400 million tons per cubic centimeter, matching the crushing weight of an atomic nucleus. But this wasn't just matter squeezed tight. It was a primordial quantum soup where the fundamental forces we know today were still fused into a single, indescribable superforce. Photons couldn't travel freely without instantly colliding with quarks and electrons in a frenzied particle ballet, creating conditions so extreme that modern particle colliders can only glimpse them in fleeting microsecond bursts. Imagine taking all the galaxies, stars, and planets that exist today, every speck of dust across 2 trillion galaxies, and compressing them into a space narrower than a DNA strand. That's the mind-bending scale we're talking about. At these densities, matter behaved unlike anything in our present universe. Quarks and gluons, normally imprisoned inside protons, roamed freely in a blazing plasma 10 billion degrees hotter than the sun's core. Even time and space lost their familiar meaning, fluctuating wildly at quantum scales where the very concepts of before and after blurred into uncertainty. This wasn't just a hot, dense state. It was a realm where the laws of physics as we know them were still being written. What's truly staggering is how rapidly this changed. Within minutes, the expanding universe cooled enough for the first atomic nuclei to form, a process called Big Bang nucleosynthesis. Yet traces of that primordial density linger everywhere. The cosmic microwave background, the afterglow of the Big Bang, carries subtle density variations that eventually seeded all cosmic structures. Those microscopic quantum fluctuations stretched across the expanding universe became the blueprints for galaxy clusters and cosmic voids. Even your body contains atoms forged in that first explosive cooling, remnants of a time when the entire universe was denser than neutron star material. This fleeting era holds answers to profound mysteries. Why does matter dominate over antimatter? What triggered cosmic inflation? The densest moments of the early universe weren't just a historical curiosity, they set the stage for everything that followed. And deep within particle colliders today, scientists recreate microcosms of this quantum inferno, hunting for clues about how a speck of infinite density became the sprawling cosmos we call home. Inside a neutron star's core, matter doesn't just reach extreme densities. It undergoes a transformation so bizarre, it defies everything we know about fluids. Here, where pressures are 100 trillion times greater than Earth's atmosphere, protons and neutrons might dissolve into a frictionless quantum soup called a superfluid. Picture liquid helium on Earth, which can flow upward against gravity in a thin film, but amplify that effect by a factor of 1 billion, and you've got the mind-bending physics at play in a neutron star's heart. Superfluidity occurs when subatomic particles sync up into a single quantum state, moving in perfect unison without any energy loss. On Earth, this requires temperatures near absolute zero. But inside a neutron star, the crushing pressure forces matter into this state even at 1,000,000 degrees. The neutrons align so precisely that they flow without viscosity, meaning a whirlpool stirred in this cosmic fluid would spin forever without slowing down. Some models suggest these currents could wrap around the entire core, creating microscopic vortices that trap mind-boggling amounts of rotational energy equivalent to a hurricane packed into a teacup. What's truly wild is how this affects the star's behavior. A superfluid core could explain why some neutron stars exhibit sudden glitches at tiny speed-ups in their rotation. As the outer crust slows down over time due to magnetic braking, the superfluid interior might resist this deceleration. When the difference becomes too great, the superfluid's vortices suddenly rearrange, transferring angular momentum to the crust like a cosmic clutch engaging. The result, a millisecond hiccup in the star's spin, detectable from light years away as a pulsar's rhythm abruptly changes. These quantum vortices aren't just theoretical, they leave fingerprints in gravitational wave signals. When two neutron stars collide, their superfluid cores might slosh violently, emitting ripples in spacetime that carry details about their internal structure. Some simulations suggest superfluidity could even delay a collapsing star's transformation into a black hole, as the frictionless fluid resists compression longer than normal matter would. But the strangest implication lies in the superfluid's ability to mimic the early universe. The same quantum coherence happening in neutron star cores might resemble conditions moments after the Big Bang, when all particles existed in a unified, frictionless state. By studying these stellar oddities, we're not just probing extreme astrophysics, we're glimpsing the universe's first microseconds, preserved like cosmic fossils in the densest objects known to science. Deep within aging white dwarfs, a slow-motion cosmic metamorphosis unfolds, one that turns these stellar embers into celestial diamonds. After billions of years cooling from their fiery origins, the intense pressure at a white dwarf's core triggers a remarkable phase change. Carbon atoms lock into an orderly crystalline lattice, effectively transforming the star's heart into a planet-sized gem. This isn't metaphorical, it's literal crystallization, where matter under extreme conditions behaves more like frozen honey than the plasma of its youth. The process begins when a white dwarf's internal temperature drops below 18 million degrees Fahrenheit, crossing a critical threshold where quantum mechanics overrides thermal chaos. Electrons, already squeezed into a degenerate state by the star's immense gravity, force carbon and oxygen nuclei into fixed positions despite the searing heat. Picture trillions of atomic nuclei, each repelling its neighbors due to their positive charges, suddenly surrendering to the pressure and snapping into a rigid formation, like a raging crowd freezing mid-motion into a perfect grid. The result, a crystalline core with properties that would make Earth's hardest diamonds feel flimsy by comparison. What's astonishing is the scale. A typical crystallizing white dwarf might contain a diamond-like mass equivalent to 300,000 Earths, compressed into a sphere no larger than our planet. The crystallization front expands outward from the core at a glacial pace, sometimes just a centimeter per year, as the star's residual heat gradually bleeds into space. Some models suggest the solidification process releases latent heat, briefly slowing the white dwarf's cooling and creating observable bumps in their temperature curves. The universe has already given us glimpses of this phenomenon. In 2004, astronomers discovered BPM 37093, a white dwarf whose pulsations matched predictions for a partially crystallized interior. Its core, roughly 90% solid, likely resembles a massive diamond wrapped in a thin shell of liquid carbon, a celestial jawbreaker with a gemstone center. Another candidate, LP40-141, exhibits spectral lines hinting at carbon crystallization so extreme. Its core may have formed a conductive metal-like structure, blurring the line between mineral and degenerate matter. This transformation isn't just cosmic trivia, it rewrites the life cycle of stars. Crystallization locks away a white dwarf's remaining thermal energy, effectively hitting pause on its cooling process for billions of years. Some crystallized dwarfs may take longer to fade than the current age of the universe, becoming frozen time capsules that outlast galaxies, and when two such stars collide, the resulting supernova could scatter crystallized carbon debris across space, seeding future planetary systems with stardust literally hardened into diamond form. Yet the most poetic detail lies in the chemistry. The same carbon now freezing into celestial diamonds was forged in a star's fiery demise billions of years earlier, a reminder that even in the cold depths of cosmic time, the universe finds ways to turn destruction into enduring beauty. Black holes don't just crush matter, they might obliterate the very information that defines it, sparking one of physics' fiercest debates. At stake is a fundamental principle of quantum mechanics. Information can never be destroyed, only scrambled. Yet black holes, as described by general relativity, appear to be cosmic shredders swallowing particles, and the data they carry irretrievably. This contradiction, known as the information paradox, pits two pillars of modern physics against each other in a battle with existential stakes. Picture tossing a book into a fire. In principle, every word could be reconstructed from the ashes if you tracked the smoke's molecular motion, but toss that book into a black hole. Relativity says it's gone forever, compressed beyond recovery at the singularity. Quantum mechanics screams otherwise. Information is immortal, woven into the universe's fabric. The conflict became undeniable in the 1970s when Stephen Hawking proved black holes evaporate over time, leaving behind only thermal radiation. If that radiation carries no trace of what fell in, the information truly vanishes, violating quantum determinism. The debate hinges on what happens at the event horizon. One camp argues quantum effects create a firewall of high-energy particles that burns up incoming information, preserving it in Hawking radiation, albeit in hopelessly scrambled form. Others propose holographic theory, where data isn't lost but encoded on the black hole's surface like a cosmic DVD, with the interior acting as a projection. The wildest idea, that black holes aren't endpoints but portals, their singularities birthing new universes where the information reemerges, rewritten into different physical laws. Recent breakthroughs add fuel to the fire. The discovery of soft hair, low-energy quantum imprints around black holes suggests information might linger near the horizon. Meanwhile, quantum computers simulate black hole dynamics, hinting at decryption methods for Hawking radiation. Yet the paradox remains unresolved, a reminder that where relativity and quantum mechanics collide, the universe guards its secrets fiercely. The answer, when it comes, won't just solve a puzzle, it'll redefine our understanding of reality's deepest layers. You might think the space between stars is empty, just a vast, uninterrupted void. But scattered across those trillions of miles are trillions more microscopic dust particles, each barely wider than a virus. Individually, they're insignificant. Collectively, they form an invisible fog so dense it shapes the fate of galaxies. These interstellar dust grains, mostly flecks of carbon, silicon, and ice, make up less than 1% of a nebula's mass, yet their impact is cosmic. They're the universe's ultimate paradox, unimaginably sparse, yet impossibly powerful. Take the iconic Horsehead Nebula. Its silhouette isn't carved by gas but by dust, a wall of particles so thick it blots out the light of stars behind it like interstellar smoke. A single grain might span just 0.1 microns, 1,000 times thinner than a human hair, but stack enough together and they'll dim a star's glow by magnitudes. This isn't just obstruction, it's creation. Dust grains act as cosmic refrigerators, radiating heat away from collapsing gas clouds, allowing them to cool and contract into protostars. Without dust, the universe would lack the cold, dense pockets needed to ignite stellar nurseries. Here's where it gets wild. These motes of dust are also molecular assembly lines. Their surfaces, roughened by eons of cosmic radiation, provide the perfect landing pads for atoms to meet and bond. Hydrogen molecules form there, then simple organics like methanol and formaldehyde. Over millions of years, these ice-coated grains grow into micrometer-sized pebbles, then kilometer-wide planetesimals. The dust that dims starlight today could be the bedrock of tomorrow's Earth-like worlds. The numbers defy intuition. In the densest molecular clouds, there might be only a few hundred dust particles per cubic meter. A vacuum cleaner would find nothing to collect. Yet across light years, that sparse sprinkling becomes an opaque curtain. The pillars of creation, their towering shapes are sculpted by dust's delicate dance with starlight, each photon nudging particles over eons like wind carving sandstone. Even our own solar system bears dust's fingerprints. Zodiacal light, that eerie glow at dawn, is sunlight reflecting off debris left by comets and asteroids, the remnants of the very dust cloud that birthed our sun. But dust's true brilliance lies in its alchemy. When massive stars die in supernova, they blast heavy elements like iron and silicon into space, where they condense into new dust grains. These then drift into neighboring nebulae, enriching future generations of stars and planets with the ingredients for rocky worlds, and maybe life. Every carbon atom in your body likely passed through multiple cycles of stellar death and dust rebirth before becoming part of you. The universe's emptiest spaces are anything but barren. In the silence between stars, dust weaves the threads of creation, proving that sometimes the smallest things cast the longest shadows. Neutron stars may burn with the intensity of 100,000 suns when born, but time is the great equalizer. Even these cosmic powerhouses will eventually fade into darkness. Imagine an object so dense it warps space itself, yet destined to become colder than the background glow of the Big Bang. Over trillions of years, neutron stars will radiate away their remaining heat, not with a bang, but with a slow, silent exhale into the void. The cooling begins with a furious pace. Fresh from a supernova, a neutron star's surface blazes at over 1,000,000 degrees, glowing fiercely in X-rays. But trapped within its crystalline crust, heat has no easy escape. The star's incredible density means energy must trickle outward through layers of neutron-rich material as sluggish as honey flowing through a sieve. For the first 1,000,000 years, neutrinos, ghostly particles that barely interact with matter, carry away most of the thermal energy, leaving the surface to cool to a mere 100,000 degrees. As millennia stretch into eons, the cooling slows but never stops. Electromagnetic radiation takes over as the primary heat leak, with the star's metallic surface emitting a fading glow. After 1,000,000,000 years, temperatures drop to 10,000 degrees, making the star dimmer than most white dwarfs. By 1,000,000,000,000 years, it may hover just a few degrees above absolute zero, its once gleaming exterior reduced to a pitch-black sphere barely warmer than the cosmic microwave background. What remains is a dark relic, an ultra-compact fossil with all its original mass compressed into a motionless, city-sized orb. Any remaining magnetic fields, once powerful enough to shred atoms, will have decayed into faint whispers. The star's rotation, initially frenetic, has long since braked to a halt, its pulsar beams silent. Even its famous density-driven quirks, starquakes, glitches, and X-ray bursts are memories frozen in time. Yet this cold endpoint isn't entirely inert. Quantum effects might still stir within its core. Some theories suggest neutron star interiors could contain exotic states like superfluid neutrons or free quarks that retain faint thermal activity far longer than the crust. Others propose that rare quantum tunneling events could cause the star to very slowly leak neutrons from its surface over timescales so vast they dwarf the current age of the universe. The ultimate fate of these dark cinders depends on cosmic evolution. If protons decay, as some particle physics models predict, neutron stars will gradually evaporate over even longer epochs. If not, they may persist until the theoretical heat death of the universe, their incredible density untouched by time. Either way, they'll outlast galaxies, surviving as the last visible remnants of dead stars in a cold, expanding cosmos. It's a humbling thought. Long after the last red dwarf flickers out, these silent, ultra-dense sentinels will drift through the dark, carrying the compressed remains of stellar fury into an era when the universe itself has forgotten what it means to shine. For a few fleeting microseconds inside particle colliders, scientists recreate the hottest, densest state of matter since the birth of the cosmos' quark-gluon plasma. This primordial soup, where quarks and gluons roam free instead of being locked inside protons and neutrons, hasn't existed naturally since the universe was a trillionth of a second old. Yet today, machines like the Large Hadron Collider smash heavy ions together at near-light speeds, generating temperatures over 5 trillion degrees, 250,000 times hotter than the Sun's core, to briefly resurrect this exotic state right here on Earth. Creating this plasma isn't just about brute force, it's a precision operation. When gold or lead nuclei collide head-on, their energy condenses into a fireball smaller than an atom but denser than a neutron star. Within this microscopic inferno, the colossal pressure melts the nuclear boundaries that normally confine quarks, dissolving protons and neutrons into a seething quantum broth. The resulting plasma behaves less like a gas and more like a perfect liquid, with virtually zero viscosity, a property so extreme it flows smoother than any substance in everyday existence. What's astonishing is how closely these lab-made fireballs mimic the infant universe. Measurements reveal quark-gluon plasma expanding and cooling almost identically to theoretical models of the Big Bang's first moments. Tiny fluctuations in its structure even match predictions about quantum ripples that eventually grew into galaxies. By studying how this plasma emits particles as it cools, physicists have clocked its transition back into normal matter at just 10 microseconds old, a snapshot of the exact instant the early universe froze into the protons and neutrons we know today. The real magic lies in the plasma's exotic properties. Unlike ordinary matter governed by electromagnetism, this quark soup operates under the strong nuclear force, the same glue that normally binds atomic nuclei. Yet at these energies, the force weakens, a phenomenon called asymptotic freedom that lets quarks move almost independently before recombining. Some experiments even suggest the plasma might conduct electricity perfectly or exhibit strange quantum entanglement on macroscopic scales, offering clues about how the universe's fundamental forces first untangled from their primordial unity. While these lab-created universes vanish in less time than it takes light to cross a proton, their legacy endures. Each collision leaves behind telltale particle patterns, like elliptical flows of debris, that act as fingerprints of the plasma's existence. Recent discoveries of strange hadrons, particles laden with strange quarks in these collisions, hint at even wilder possibilities, including temporary formations of exotic matter like quark molecules. Some theorists speculate that quark-gluon plasma might still lurk at the cores of neutron stars, where pressures approach those of the early universe. These experiments do more than satisfy cosmic curiosity. They stress-test the very foundations of physics by recreating conditions where quantum mechanics and relativity collide. Quark-gluon plasma studies probe questions about mass creation, the nature of force carriers, and why matter dominated over antimatter in the early cosmos. Every micro-fireball is a time machine, offering a glimpse into the universe's most transformative instant and proving that sometimes, to understand the enormity of space, we must first master the secrets hidden in the infinitesimal. When a star dies, most people picture a supernova, an explosion so bright it can outshine entire galaxies. But there's something even more extreme lurking in the cosmos, the hypernova. This isn't just a bigger blast, it's a fundamentally different kind of stellar death, where the star's core doesn't just collapse into a neutron star, but keeps imploding with such violence that it bypasses all intermediate stages and forms a black hole instantly. The difference is like comparing a firecracker to a thermonuclear bomb. Both are explosive, but one operates on a scale that defies intuition. The key lies in the star's initial mass. While a typical supernova occurs when a star between 8 and 20 solar masses exhausts its fuel, hypernova arise from stars so massive 30 solar masses or more that their cores can't even stabilize as neutron stars. When these behemoths collapse, gravity's grip is so overwhelming, the core's density skyrockets past neutron degeneracy pressure in milliseconds, crushing matter straight into a singularity. No bouncing shockwave, no lingering neutron star remnant, just an immediate transformation into a black hole, with the infalling material releasing so much energy. It powers jets of plasma moving at over 99% the speed of light. These jets are what make hypernova visible across the universe. Unlike the spherical explosions of normal supernova, hypernova channel their energy into narrow beams along the star's rotational axis, focusing their fury into gamma-ray bursts, the most luminous electromagnetic events known. One such burst, JABI 080319b in 2008, was briefly visible to the naked eye despite originating 7.5 billion light-years away. That's energy equivalent to the sun's entire 10 billion-year output compressed into a 30-second flash, but the real terror lies in the aftermath. While a supernova leaves behind a neutron star or small black hole, hypernova birth black holes with masses 20 to 50 times that of our sun, sometimes even spinning at near light speed. These aren't just denser, they're hungrier, capable of shredding stars whole and powering quasars that outshine galaxies. And because hypernova forge elements like gold and platinum in far greater quantities than ordinary supernova, they're likely the primary cosmic foundries for the heaviest atoms in the universe. The universe rarely does things halfway. With hypernova, it takes the concept of density to its logical extreme, proving that when a star's core has no escape route left, it doesn't just die. It transforms into something infinitely darker. Some neutron stars don't just emit steady pulses, they sing. When these ultra-dense stellar corpses pull gas from companion stars, the infalling material doesn't land with a quiet splat, but creates X-ray harmonies that reveal secrets about surfaces smoother than anything in the known universe. As gas spirals down at nearly half the speed of light, it slams into the neutron star's surface with enough energy to heat atoms to hundreds of millions of degrees, creating X-ray hotspots that flicker like cosmic strobe lights. But here's the twist. Those X-rays don't just beam straight into space, they skim along the star's surface, bending through its unimaginably strong gravitational field before escaping at subtly altered angles. The result, ghostly echoes, delayed X-ray flashes that carry precise information about the star's size, mass, and most remarkably, the molecular perfection of its surface. The numbers behind this smoothness are staggering. If you could shrink a neutron star to the size of a marble, its tallest surface imperfections would measure less than the width of a human hair, far smoother than any mirror manufactured on Earth. This flawless finish comes from gravity's relentless crush. The star's million-strong surface gravity pulls any protruding atoms back down almost instantly, like cosmic sandpaper erasing every microscopic bump. When X-rays ricochet off this impossibly level plane, they create interference patterns detectable by space telescopes like NASA and NICER. By analyzing these echoes, astronomers have measured neutron star radii with unprecedented precision, revealing some are barely 12 kilometers across yet pack more mass than our Sun. What's truly mind-blowing is how these echoes expose the neutron star's internal structure. The delay between the initial X-ray burst and its echo reveals how far the photons traveled along the surface, a distance that depends on how severely space-time warps near the star. Some echoes suggest certain neutron stars have ultra-thin atmospheres just centimeters deep, where incoming particles create splash zones smaller than a football field. Others hint at mountains not of rock, but of pure nuclear material where magnetic fields pin the crust into microscopic deformations no taller than a pencil lead, yet weighing more than Everest. These cosmic echoes aren't just scientific curiosities, they're stress-testing Einstein's general relativity in extreme environments. When X-rays skim so close to a neutron star's surface, they experience time dilation so extreme that a millisecond delay in their echo can reveal whether space-time behaves exactly as predicted near such dense objects. Some recent observations have even detected echoes with peculiar timings that might hint at new physics beyond our current understanding of gravity. The most poetic detail, these X-ray harmonies are fleeting. As the neutron stars feast on companion gas slows, the echoes fade, leaving behind only the star's steady spin and the memory of its brief, brilliant song etched in telescope data. But for those moments when the universe aligns just right, we get to hear a dead star whisper its secrets through the language of rebounding light. Black holes might hide an invisible inferno at their edges, not the tranquil passage relativity predicts, but a searing barrier so violent it scrambles the laws of physics. This is the firewall paradox, the idea that the event horizon, rather than being an unremarkable point of no return, could be a lethal wall of energy capable of vaporizing anything that crosses it. The controversy stems from a cosmic catch-22 when quantum mechanics collides with Einstein's general relativity. The math demands either that information about infalling matter gets destroyed, violating quantum theory, or that a firewall burns it up at the horizon, defying relativity's prediction of no drama for a free-falling observer. Picture this: as you approach a black hole's event horizon, you'd expect to feel nothing unusual, at least according to Einstein. But if firewalls exist, you'd instead hit a Planck-scale layer of ultra-high-energy particles, a boundary hotter than the core of a supernova. The energy here wouldn't just kill you, it would disassemble your atoms into a quantum fog before you even reach the singularity. What creates this theoretical blaze? Entanglement, the quantum link between particles. As Hawking radiation carries information away from the black hole, it could sever the entanglement bonds between infalling and outgoing particles, releasing enough energy to ignite the firewall. The implications rewrite black hole thermodynamics. Instead of a smooth space-time warp, the horizon becomes a physical boundary where the universe enforces quantum censorship, destroying information to preserve cosmic rules. Some models suggest firewalls might only flare up when the black hole is old and evaporating, like a security system activating during a meltdown. Others argue they're artifacts of incomplete physics, and a full quantum gravity theory will show horizons as calm as relativity claims. The debate is so heated, it split physicists into camps: Team Firewall versus Team No Drama. But here's where it gets twisted. If firewalls exist, they might not be static curtains but flickering phenomena, quantum fluctuations so extreme, they briefly manifest as walls of energy. Imagine the horizon shimmering like a heat mirage, sometimes letting matter slip through unscathed, other times annihilating it. This could explain why we've never detected firewall signatures. They're intermittent, vanishing as quickly as they form. Paradoxically, the same math that predicts these firewalls also suggests they're avoidable. If you approach the black hole in free fall, the firewall might move out of your way, like a cosmic sleight of hand preserving relativity's predictions for certain observers. The real stakes: firewalls threaten our understanding of spacetime itself. If the horizon isn't smooth, the very idea of falling into a black hole becomes meaningless. There's no inside to reach. This could mean black holes are more like holograms, their interiors projected from information encoded on the surface. Or perhaps firewalls are nature's way of marking a boundary between our universe and whatever lies beyond the singularity. Until we bridge quantum theory and gravity, this paradox remains a blazing frontier, one that forces us to question whether the universe's most extreme objects are doors, prisons, or something far stranger. Wormholes aren't just sci-fi shortcuts through space, they're hypothetical tunnels where the fabric of reality folds back on itself, and at their throats lies a pinch point of impossible density. Picture a black hole's singularity, but instead of crushing matter into oblivion, this ultra-dense nexus acts as a cosmic turnstile, threading space-time like a needle through folded cloth. The catch: holding such a tunnel open demands something even stranger than gravity's crush: exotic matter with negative energy density, a substance that defies everything we know about physics. The math behind this is both elegant and mind-bending. Einstein's equations allow for wormholes as valid solutions, but they'd collapse instantly without a stabilizing force. That's where exotic matter comes in. Unlike normal particles, which obey the classical energy conditions and create attractive gravity, this theoretical material would generate repulsive gravity, propping the wormhole's throat open against the crushing weight of spacetime trying to snap it shut. The required density at the throat, comparable to a black hole's event horizon, compacted into a ring just wide enough to permit passage. A single teaspoon of this region might contain enough compressed energy to power a star for centuries. What would crossing such a throat feel like? If exotic matter did its job, you'd experience tidal forces milder than a black hole's no spaghettification, but still a harrowing ride. Light from both ends would lens dramatically around you, creating a kaleidoscope of distorted stars as space stretched and compressed like taffy. Time dilation would warp your journey too. Minutes inside might equal years outside, making the wormhole a time machine as much as a teleporter. The real danger lies in instability. Even a slight imbalance, a single particle of regular matter touching the throat's walls, could trigger a catastrophic collapse, snapping the tunnel shut mid-transit and leaving no trace of your passage. The wildest twist, wormhole throats might not be purely hypothetical. Quantum mechanics hints at fleeting, microscopic wormholes popping in and out of existence in the vacuum foam, their throats smaller than atoms. Some theories even suggest the universe's expansion could have stretched one such wormhole to macroscopic scales in the distant past. If so, its throat could still linger somewhere in the cosmos, a relic of primordial physics waiting to be found. Whether cosmic accidents or engineering projects of an advanced civilization, wormholes represent density pushed to its most creative extreme. They're not just crushing matter into submission, they're bending the rules to build bridges across the stars. And if they exist, they'd prove that in the universe's playbook, even the most unforgiving densities can serve a purpose beyond destruction. From neutron stars to black holes, we've seen how cosmic densities can warp reality. But what about the ultimate fate of the universe itself? Will the relentless pull of gravity one day reverse the Big Bang, crunching everything back into a singularity? Or will dark energies push win out, stretching matter so thin that galaxies become isolated islands in an ever-cooling void? This cosmic tug of war hinges on a single number, the universe's critical density, the precise balance between expansion and collapse. Right now, observations suggest dark energy is winning. Distant supernovae reveal the universe's expansion accelerating, with galaxies fleeing from one another faster each passing eon. If this continues, densities we marvel at today, neutron star cores, black hole singularities, will become relics of a bygone era. In 1 trillion years, the Milky Way stars will burn out, black holes will evaporate via Hawking radiation, and even protons may decay, leaving behind only diffuse subatomic particles drifting endlessly apart. The last civilizations might gaze upon skies devoid of any neighboring galaxies, their light stretched beyond detectability as space itself becomes an ever thinner soup of quantum fluctuations. But there's another possibility, one where gravity fights back. If dark energy weakens over time or the universe hides more matter than we've detected, expansion could slow, halt, then reverse. Galaxies would begin rushing toward one another, their collisions triggering new star formation amid escalating temperatures. Over billions of years, matter would compress into a fiery maelstrom, densities soaring until even black holes merge into a single, all-consuming singularity, the Big Crunch. Some theories suggest this singularity might rebound into a new Big Bang, birthing another cycle of universes in an endless cosmic heartbeat. The most haunting scenario lies between these extremes, the Big Freeze followed by quantum decay. Here, expansion never reverses, but quantum tunneling allows spacetime itself to disintegrate over unfathomable timescales. Random quantum fluctuations could spawn new, bubble universes with different physical laws, while our own cosmos fades into absolute zero. Even the densest objects would eventually evaporate, their information scrambled into nothingness, the ultimate victory of entropy over structure. Yet hidden in this cosmic endgame is a profound irony. The same extreme densities that shape galaxies today may hold the key to our universe's survival. Some models propose that vacuum decay, the very process that could erase reality, might be thwarted by black holes' immense gravity, creating pockets of stability where information persists against all odds. Others suggest dark matter's clumping could seed new universes within black hole singularities, turning these destroyers into cosmic midwives. Whether the universe ends in fire, ice, or rebirth, one truth remains: density isn't just a property of matter, it's the architect of time itself. From the quark-gluon plasma of the Big Bang to the last evaporating black hole, the cosmos writes its story in collisions and collapses, expansions and erasures. And somewhere in that story, we're here brief witnesses to the fleeting era when stars still shine, black holes still devour, and the universe's grand fate hangs in the balance between two infinites. From neutron stars where a teaspoon of matter outweighs mountains to black holes that twist space and time into oblivion, we've journeyed through the universe's most extreme densities, places where physics as we know it bends until it breaks. Think about this. At the heart of a magnetar, magnetic fields are so strong they could rip atoms apart from thousands of miles away. Or that quark stars might exist, where matter shatters into its most fundamental building blocks like a cosmic jigsaw puzzle pulled apart by gravity's unstoppable grip. And let's not forget the Big Bang singularity itself, where all the energy in the cosmos was once crammed into a space smaller than an atom, hotter and denser than anything we can recreate. But here's what's truly wild. These aren't just abstract ideas. They shape the cosmos in ways we're only beginning to understand, the gold in your jewelry. Forged in the violent collisions of neutron stars, the galaxies we see, sculpted by dark matter's invisible density weaving the cosmic web. Even the atoms in your body were once squeezed and fused in the hearts of stars that no longer exist. Density isn't just a number, it's the universe's way of testing the limits of reality. So which fact left you speechless? Was it the starquakes on neutron stars, where mountains the height of a pencil lead way more than Everest, or the photon sphere around black holes where light gets trapped in an endless loop? Drop your pick in the comments. I want to hear which cosmic extreme blew your mind the most. And if you're hungry for more mysteries, from the quantum foam of spacetime to the secrets of dark energy, hit subscribe. The universe has plenty more surprises waiting, and I'll be here to unpack them with you. Until next time, keep looking up. The cosmos is far stranger than we've